Good evening, everyone. Okay. So in the first class, in the that is last class, we started introduction of transformer first. Then we have seen about Faraday's law and then Lenz's law. Okay. Now let's see about dot convention in transformers. How to place dot in primary and secondary windings of transformer. We will see now. Right. Next one. Dot convention in transformer. So marking dots, that is polarity marking of transformer windings is very important, which is required only for parallel operation of transformer. And there is no other use of these dots or polarities. Suppose there is a transformer, primary side, any side you given supply, and other side you need to connect load. For any two terminals, you can connect load. You no need to check any polarities there. Any terminals you can directly connect to the load. But what is the need of this dot convention? Only for parallel operation of transformer. So we have many transformers operating in parallel. No, all the transformers operating in parallel only outside distribution transformers or transmission transformers, anything. So for that reason, to operate two transformers in parallel, the most necessary condition is polarity. That is dot polarity. So for that reason, we need to mark exactly the dots here first. If dots is marking is mistake, definitely you will get severe short circuit currents while operating in parallel operation. Okay. For that reason only dot convention we are considering now. Dot convention. How to place polarities for primary and secondary winding, we will see now. Observe. So first I will consider a simple diagram, then we will apply this is for transformers. Okay. First I will take a small iron core, just like statical induced EMF. Now we taken two coils magnetically coupled. In the same way, I'm taking now that this is coil 1, let it is coil 2. So this dot convention or whatever the dots we are placing, it is completely based on Lenz law only. Based on Lenz law only, we are placing dots here. Now I will tell one important point here. That is, every time we are writing EMF induced in the winding E equal to, that may be primary or secondary. How we are writing? Minus N d phi by dt. Like this we are writing now. And most of the people ask when we need to write this minus. And what happen if we don't write minus? Yes, we have to write minus at one condition, and we no need to write that minus at one condition. So when it is, I will tell now clearly. Observe. Based on Lenz law only, we are placing dots here. So observe. So first we taken two coils, coil 1, coil 2, and which are magnetically coupled. Now to one of the coil we need to give supply. Then only flux will produce. No? So we are giving supply to one of the coil. Let coil 1 it is. I'm giving supply to this some voltage having frequency here. When we give supply, a current will flow here. Let the current here is I1. Now current I1 will flow like this based on the sense of winding it is. Okay, like this current is circulating in the coil. Now apply right hand thumb rule here. Four fingers is current direction, thumb finger is flux direction. Now when we apply, the flux direction I'm getting in this direction. This is the direction of flux. Okay, in this direction I'm getting flux. By applying right hand thumb rule, it is four fingers current direction and thumb finger is flux direction. Now same flux I will continue, same direction, just I will complete the path. Okay, like this flux is flowing. This is the direction of flux. Up to here, we know already it is. Now, how to mark these dot polarities for both primary and secondary winding. So always the primary side. Primary winding means what? Wherever you give supply. So that primary winding is directly you can put dots based on your interest. That is like see, there is one statement for this to put the dot polarities. If you remember this enough, you can answer any type of question based on these dot polarities. That is, first write the statement. Write the statement first. If current enters at dot, if current enters at dot on primary, then current should leave at dot. Then current should leave at dot on secondary. So this is primary winding. I'm treating like primary winding and secondary winding, or you can call coil 1, coil 2. Okay. With respect to transformer point of view, I'm writing this statement here. If current enters at dot on primary, then current should leave at dot on secondary to satisfy Lenz's law. So based on Lenz's law only, we are writing this statement. Now I will consider Lenz's law. What is Lenz's law? Yesterday we have seen. No? What is Lenz's law? What is the Lenz's law? According to Lenz's law, it states that the EMF induced in the winding will produce a current, and that current will produce a flux. That flux must be opposite to main flux. This is our main flux. Whatever flux produced due to source, that is main flux. Now secondary side, second coil it is. When you connect a load here, a current will flow in this. When you connect a load, a current will flow. And in what direction current will flow? Can you put directly current direction? No, you should not put. Automatically current will flow such that how it will flow? It will flow such that it will produce a flux. That flux is opposite to main flux. So always what you have to remember according to Lenz's law, the flux produced by secondary winding or second coil should be opposite to primary flux or main flux. So this is the main flux. This dotted blue dotted line is what? Main flux it is. This is main flux. Now we have to produce a flux exactly opposite to this. So this is the flux it should produce. Now in order to produce the flux in this direction opposite to main flux, apply right hand thumb rule. Flux is in this direction. Apply right hand thumb rule. Flux should be in this direction opposite to main flux, and apply your 4 fingers. However, your 4 fingers are curling in the same direction, current should flow in the coil or winding. How it is? Now, if I apply my 4 fingers, so going inside, coming outside, means to the front side of me, the current is coming downward direction, like this, in the coil. Then apply to the load, how it is coming. See, this is upper side, so current will come directly outside, and it will go inside here. So current direction I mark. How I mark current direction in the second coil? By applying Lenz's law. How the flux produced due to this winding should be opposite to main flux. That's why I taken this is opposite to main flux. Okay, main flux is right to left, and this flux due to secondary winding is left to right. So I am applying right hand thumb rule in the direction of flux. Thumb is flux direction, and 4 fingers is current direction. Then if you apply, this is the current I got. Then what is the statement here I given? According to Lenz's law only. If you apply this, and you no need to draw all these flux lines here. So apply here. If current enters at dot on primary, so you can take anything on primary side. For primary winding or first coil, you can take anything. Means, so I'm considering current entering here. No, see, into the coil 1, current entering here. So I will assume that this is my dotted terminal. This is my dotted terminal, primary side. Secondary side, I need to mark. So what is the statement? If current enters at dot on primary, then current should leave at a dot on secondary side. Now where current is leaving second coil, observe. second coil where current is leaving the coil here. No, current is leaving here. So this is my dotted terminal. Primary side, this is the dotted, current enters. Secondary side, current is leaving. This is my dotted terminal. So like this, we need to mark these dots. Dot polarity marking, very, very important. If by mistake it is wrongly marked, then while operating in parallel, definitely you will connect two transformers wrongly, so that severe short circuit currents will flow. So this is one statement. Other statement is, if current leaves at dot on primary, opposite to this, any one, if you remember enough, no need to remember both. Okay. Other statement is what? If current leaves dot on primary, where it is leaving? Where it is leaving? Here it is leaving. Okay. Here it is leaving. You can consider this is dot. Current leaving dot. Current leaving at dot on primary side. Current is leaving the dot on primary side. Then what should be secondary? Current should enter the dotted. Current should enter at dot on secondary side. So to avoid all this confusion, remember any one statement. This is the best statement enough. What is that? If current enters at a dot on primary side, then current should leave at a dot on secondary side. Okay. So I taken primary side, current entering here. That's why this is I placed dot. Now secondary side, based on Lenz's law, I marked current, and then I am observing where current is leaving this coil, second coil, here. That's why I placed here. If current enters at dot on primary, current should leave at dot on secondary side. Then it is satisfying Lenz's law. Okay, based on Lenz's law only we are placing dot polarities. Directly you should not say this is dotted terminal without marking current here. Okay. So dot polarity important for some of the questions. If you don't know about dot polarity, you cannot answer that question first. So I will give that question also. So take all of you. Take the statement. If current enters at a dot on primary, then current should leave at a dot on secondary to satisfy Lenz's law. Suppose if you take both same, no, current entering at a dot on primary and current entering at a dot on secondary, then it is wrongly marked polarity, because while operating in parallel, now you cannot understand, and most of you asking what is the need of this dot polarity first. What is the need of dot polarity? At the starting itself I said this dot polarity is required only for parallel operation of transformer. Suppose if you want to operate two transformers in parallel, one of the condition is polarity of two transformers should be same. Otherwise, short circuit currents will flow. So to avoid that problem, dot polarity we need to mark first before connecting in parallel. Okay. Only for parallel operation, dot polarity is required, and there is no other use of this. There is no other use. Dot means you can consider positive or negative. Generally, we consider dot means plus, undotted means minus. But do you have plus minus terminals in AC? No. Generally, we consider dot means like plus and undotted means minus. Okay. Hmm. Now let's see what type of questions you will get on dot convention. So I will give one example. So first I will give one transformer diagram now directly. Now you try to mark where is dot polarities. Okay. See this. So I'm giving transformer diagram. So you need to mark the polarities for the two windings. Okay. primary side I'm giving supply V1 having frequency F. Now a current is flowing, let it is in this direction, current is flowing. Okay. Now I'm considering according to statement, current enters at dot on primary means current should leave at dot on secondary side. Now I'm taking current enters at dot on primary. This is my dotted terminal. Now secondary side, this is A, this is B. Now tell me which one is dotted terminal, A or B? Secondary side, which one is dotted terminal, A or B? Okay, right. Okay, observe. So most of you said A and some of you saying B also. Now see here which one is right. Okay, enough. Enough. Observe. How to mark dot polarity on secondary side? First, you need to mark main flux direction. Main flux. Now you take in primary side, this is the direction of current now. So current enters at dot. And what is the direction of flux? Apply right hand thumb rule on primary side. Then if I apply direction, right hand thumb rule, this is the direction of flux. Right hand thumb rule is applied, primary side. Flux is coming in upward direction. So same flux direction I'm considering throughout the core. Okay, this is direction of flux. Main flux it is, or primary flux you can call. So main flux is flowing in this direction in second coil. So this second coil, according to Lenz's law, it should produce a flux opposite to this main flux. No? So you take flux opposite. Opposite means upward direction here. Opposite to main flux. Now flux in the secondary side is upward direction. Apply right hand thumb rule again here. Apply right hand thumb rule on secondary side. Then if you apply, so flux is in upward direction, thumb indicates flux and four fingers indicate current. Now you apply the four fingers, current direction I'm getting in this way in the second coil. Now here current will go inside. According to the sensor finding, current will come outside here. Now what is the statement? If current enters at dot on primary, current should leave at dot on secondary. Now where current is leaving? At A, current is leaving the winding. So this is the dotted terminal. A is correct. Okay, not B. At B, current is entering. Current is entering at B in the coil and leaving at dot. Okay. Next, one question I'm giving. Try to answer this. So how the questions we get in dot polarities like this. So they will give some number of windings on transformer. So just I given two windings. Now I will give three windings here. So for one winding I will give supply and remaining two windings I just left, and you need to answer what is the voltage here. See this. This is one winding. Second winding. Third winding. So to this first winding or primary winding, secondary winding, tertiary winding, like this. Now to the first winding I'm giving a voltage supply here. Let this is 100 volts. Supply is given. Now the voltage across this is directly I'm giving this is let it is 50 volts and let it is 70 volts. Okay, voltage ratings directly given for three windings. Now I will join like this. I will connect these two windings in this way. Now you need to answer here. Let it is X and this is Y. Now what is the voltage across X and Y? Tell me. What is the voltage across X and Y? What is the voltage across X and Y? This is the figure I given. What is the voltage across X and Y? Magnitude only. Magnitude is how much? Is it 50 plus 70 or is it 70 minus 50? So don't tell directly 50 plus 70 because that may be additive polarity or subtractive polarity. So people will think that here 50 volts is there, here 70 volts is there. Directly they will tell 70 plus 50, 120 volts. So it may be additive or it may be subtractive also. That is 70 minus 50 also you may get. That is 20 volts. So that depends on this dot polarity. So for that reason, you need to mark dot polarity for each coil first, each winding first, and then check how they are connected in additive or subtractive. Simple, same as this first figure. However, we mark polarity, you also mark polarity for each winding first, second winding and third winding, and then check they are connected in additive or subtractive. Okay, only magnitude, that may be plus 20 or minus 20, only magnitude I want. 20 volts or 120 volts. Yes, observe first. First mark main flux direction. So the figure is this. Current is entering at dot on primary here. So based on the direction of current given, what is the flux direction? Flux direction, apply right hand thumb rule, upward direction. This is the direction of flux by right hand thumb rule. Now same direction, continue. This is main flux direction. Okay, main flux is drawn. Now what should be the flux due to other coils? There may be two coils or three coils or any number of windings. Same procedure. Now there are two windings here. The two windings should produce a flux opposite to main flux. So it should produce a flux opposite to main flux. It should also produce a flux opposite to main flux. So first flux is marked opposite. Now apply right hand thumb rule at each winding. First second winding, that is 50 volts. Flux is flux opposite to main flux. Flux produced by second winding is opposite to main flux. Then right hand thumb rule is applying. Thumb indicates flux, four fingers indicates current. So I'm applying four fingers. So I'm getting current in this winding like this. Okay. So only in the winding I mark. Now come outside. So this current directly will come outside because this is upper surface and it is from the bottom, it is coming, going inside and like this. Okay. This is direction of current. Okay. Now where is the dot polarity for second winding? If current enters at dot on primary, current should leave at dot on other winding, not only secondary. For secondary winding or tertiary winding, or if there is fourth winding also, current should leave at dot only. Now where current is leaving? Here, X. So this is the dotted terminal. Okay. For second coil, dot is here. Next, for third coil or third winding, this is flux direction opposite to main flux. Apply right hand thumb rule. Flux should be upward direction. Then apply your four fingers. So current I am getting like this. Direction of current in the winding by right hand thumb rule. So this current will come directly outside and it will go inside. Now where current is leaving? Third winding here. That is this is the dotted terminal. If current enters at a dot in primary, current should leave at a dot in second winding and third winding, both the. Okay. Now dots is marked. So dot means you can take plus or minus anything. So I'm taking plus. This is minus. And here dot means plus and this is minus. Now observe once, minus minus is connected. When the voltage will be additive? When you connect one battery terminal with other battery with opposite polarities, plus minus, then it is additive, like this. Let it is 4 volts and it is 2 volts. What is the resultant voltage? 6 volts. Additive it is. Minus is connected with plus. Otherwise, if minus minus is joined, then it will become subtractive polarity. Okay. Now, in the same way, here also minus minus is connected. Definitely, it is subtractive. Therefore, Vxy equal to magnitude I'm taking 70 minus 50. This is 20 volts. Okay. Like that, if there are four windings and based on they connected, polarity is connected, you need to check whether it is additive or subtractive. Okay. Don't say directly 70 plus 50 120 volts. Clear? This type of questions we get from dot polarities. Completed all of you? No, so this current individually we are marking. Actually, if you connect load, current will flow only in one direction. Only we are considering for polarity marking it is. Okay. Yes. Yes. Now I will tell. See, observe this figure. First one. If it is required to write equation now, EMF induced in the secondary winding E2. Now you should not write minus. You should write only N2 into d5 by dt. Don't write minus now. See, in this for this diagram, first one I'm saying, because based on the Lenz's law, already you marked polarities here. So once you marked polarities, you no need to write minus here. Again, if you write minus now in this equation, that is wrong. Don't write minus now. When we have to write minus, suppose polarities are not marked here, then you have to take minus in the equation. Okay, any one only. Already you applied Lenz law, then you should not take again the minus sign in the EMF equation. Clear all of you? So make a note. Make a note. Once the dot polarity is placed, once the dot polarity is placed, once the dot polarity is placed, then it is not required to take negative sign. Then it is not required to take negative sign in EMF equation. Then it is not required to take negative sign in EMF equation. Yes, some of you asking in second, this is second coil, this is third coil, this is first coil. Some of you asking in second and third, current is leaving in both. Yes, what I said, if current enters at a dot in primary winding, current should leave at a dot in secondary. That is for only two windings I said. Suppose if there are three windings or four windings, what is the statement? If current enters at a dot in the source winding or primary winding, wherever you connect source, then current should leave at a dot in all other windings. For all other windings, it will be same. Okay. Second coil, third coil, or if you place one more coil here, then in that coil also current should leave at dot only. Only in the source winding or source coil, current should enter. Remaining all current should leave. Okay. Now see one more. Suppose there is a transformer. Okay, primary side source is connected. Let some voltage V1 F, and they will give polarity, dot polarity. Current also they don't indicate. That is your wish. You can take current is entering at dot or current is leaving at dot. Anything. Generally follow current enters at dot in source winding. Now, if it is not mentioned anything about polarities and it is asked to find EMF induced, then secondary side E2, primary side E1. So EMF induced means mostly you need to find secondary side only. Then E2 equal to, what is the equation now you have to take? It is having number of turns N1 and it is having number of turns N2. Then what you will write? Then you have to take minus N2 into d5 by dt. Okay, then whatever you will get, that is correct. But once you marked polarities here, now polarities are not marked in this, so you have to take minus sign in the EMF equation. Suppose if polarities are marked like this, if polarities are marked, then you should not take minus sign. So now I am marking polarities in this. Polarities are marked. Now what is the EMF induced? E2 equal to N2 into d5 by dt only. You should not write minus here. That is wrong, because already there is Lenz law. Based on Lenz law only polarities are marked here. Already based on Lenz law polarities are marked. EMF polarity. Okay, then you should not take minus sign in this. This is correct. And for this figure, this is correct. Okay, when there is polarity marking in the figure, you no need to take minus sign in the EMF calculation. If there is no polarities, then you need to take, because Lenz law you need to apply in transformer, and once you applied in figure, you no need to take in equation again. Okay, if you take in both, no, then it will be wrong. The magnitude of EMF you will get wrong. Let's see one more question on this polarity marking. See the question. Generally for transformer or for this type of circuits, no, if there are three windings, we don't give supply to two windings here. Only one winding we will give supply. If you give supply to two windings, then we cannot judge the polarities for third winding, because uh, for two windings, if you give supply, primary winding supply polarity is different and secondary winding supply polarity is different. So it is not possible. You should not give supply to two windings at a time. Only one winding we have to give, and remaining winding we will utilize. Okay, so don't think like this. See, all your doubts will be cleared once EMF equation is over. Okay, not necessary. See this question. See this question. In each of the following diagrams below, instantaneous polarity of primary winding of an ideal transformer is shown. Now, in the first question, direction of flux in the core. So there are four figures, A, B, C, D. Four transformer figures are there. You need to mark flux direction in the core first, based on the given polarity on primary side. Primary side AB, plus minus indicated. Actually, plus minus we don't have. Plus minus means you can consider plus is dotted terminal. Plus is dotted terminal. Primary side they will give. Secondary you need to mark. Okay, without primary we cannot mark on secondary side. Primary they are giving, and secondary side CD, which one is dotted terminal, you need to mark. That is second question. Polarity of instantaneous voltage on secondary side polarity. This is second question. First question is what? Direction of flux. So mark the direction of flux in each figure. So you take separately four diagrams, A, B, C, D, and in each figure you need to mark flux direction by applying right hand thumb rule. Simple. So current enter set dot I am following. So I will take current enter set dot in all figures. Current enter set dot, enter set dot, enter set dot. Now observe how current will flow in the winding here. So this is upper side. So directly current will go here. This is direction of current. Okay. This is direction of current. In each diagram, direction of current. But observe in the C, that is figure C, this current will go from back side. So, and front side current will come like this. This is direction of current. Sense of winding is changed here. Next, D, figure D, and coming from the back side, it is also. This is the current direction. Now, once you know current direction, you will get the flux direction easily by applying right hand thumb rule. Apply the right hand thumb rule for first figure. So, if you apply right hand thumb rule, so I'm getting direction of flux clockwise. This is clockwise because current direction is like this and thumb will be upward direction. Then it is a clockwise direction. So here the flux is clockwise. Direction of flux you need to write clockwise. And for second one also clockwise only by applying right hand thumb rule. This is also clockwise. And C and D, figure C and D, observe the current is reverse. Current is like this and apply your right hand thumb rule. The thumb indicates flux direction, which is downward direction. So here the flux will go in downward direction. This is anti-clockwise direction. The flux in the third one is anti-clockwise. And fourth one also anti-clockwise. Okay, anti-clockwise direction. So direction of flux is marked first. Now polarity you need to mark on second side. Second question is what? Polarity marking. Now try to mark the polarities based on Lenz's law. So this is main flux. Whatever these blue color lines we drawn here, clockwise, anti-clockwise, this is main flux direction. Then what should be the flux due to secondary winding? Opposite. So take opposite. The flux due to this one should be opposite. This is also opposite. This is upward direction, so it should be downward direction, opposite. The flux due to secondary winding opposite to main flux. Okay. Now apply right hand thumb rule according to this flux direction. You will get current direction. Apply here for second for figure A. First one, for the first one, flux should be upward direction due to secondary winding. So apply your 4 fingers. Apply carefully. So I'm getting the current is in this direction. You take little big figures. This is the current direction I'm getting. So current will come directly outside and goes inside. Apply right hand thumb rule and mark the current direction. For second figure also, flux should be upward direction. This red line, flux is upward direction, which is opposite to main flux. Main flux is downward direction. So applying right hand thumb rule here, getting the current in this direction. So you take little big diagram. Okay. Current will come outside directly and goes inside. And for third diagram, flux is downward direction. Red line is downward direction. So apply the 4 fingers. In this direction, current is coming. So it goes inside and comes outside from here. Similarly for fourth one, flux is in downward direction. Applying right hand thumb rule, current is like this. And it goes directly and comes back. Okay, current direction is marked on secondary side by taking flux opposite to main flux. Now for each one, first current enters at dot on primary, current should leave at dot on second. So D is the dotted terminal. D, small d is the dotted terminal. Next, second figure. Current should leave at dot. C is the dotted terminal. And for third diagram, current enters at dot on primary, current should leave at a dot. C is the dotted terminal. Fourth one, D is the dotted terminal. Current should leave at dot. So different sense of winding is given. Same transformer, different sense of winding on primary and secondary. So with respect to that, polarities are changed. Okay, clear all of you this? Uh, Mamata, why in the CD, figure CD, flux is in anti-clockwise? Why flux is in anti-clockwise? Because observe, primary side, I taken current enters at dot. Now observe, primary sense of winding is changed. From the back side, current is coming, it is. Now, if you apply right hand thumb rule for primary winding, the flux I am getting downward, downward. That's why same direction I continue. So anti-clockwise we are getting. Clear? Okay. Next, one more question. One more question. See this. Read the question. A, B, and C are the three windings of a transformer having 200, 100, and 60 turns, respectively. When a voltage of 100 volts is applied across A, so there are three windings ABC, across A 100 volts is applied. Find the voltage that develops across X1. This is X, this is Y. So here the voltage is how much? Vx1. Calculate. Just like previously we solved one example. DC connected, but how it is connected not given. Additive or subtractive. You need to answer what is Vx1. Okay, primary side dot is not mentioned, so you consider this is dotted terminal. So current enters at dot on primary like this. Now try to answer. Current enters. Current enters at dot on primary. Primary you can take anything, you can take based on that secondary side you will get the voltage. So take little big diagram so that all flux directions you should not confuse again if you see after 1 month also. See, transfer winding A having 200 turns, winding B having 100 turns, winding C having 60 turns. Now, if you observe here, 100 volts is applied to winding A, which is having 200 turns. Then, what is the EMF per turn or voltage per turn? Tell me. With respect to this winding A, what is voltage per turn? 100 volts is applied to 200 turns. Then what is voltage per turn? 0.5. Okay, voltage per turn is 0.5. So first of all, you should know this point. Actually, it will come in EMF equation. So before that, this question I given based on dot polarity. So you remember this point is in a transformer, voltage per turn is same for all the windings. Any number of windings, voltage per turn is same. So how much voltage per turn we got based on the primary side? 0.5. So for remaining winding also, voltage per turn is 0.5 only. Okay, voltage per turn is 0.5 volts in this transformer. Now transformer B having 100 turns. Transformer B having 100 turns. Then what is the voltage of winding B? Winding B having 100 turns. Then what is the voltage? 100 into 0.5. So 100 into 0.5, 50 volts. Because voltage per turn is 0.5 volts. 100 turns means 100 into 0.5, 50 volts. Similarly, winding C, third winding, having 60 turns. So 60 into 0.5, how much it is? 30 volts. Okay. So B winding voltage is 50 volts. C winding voltage is 30 volts. Then you may get 50 plus 30, or you may get 50 minus 30 based on polarities, additive or subtractive. So what is the answer? Okay. So most of you saying 20, 80 volts. First mark polarities, then you will get the exact answer, additive or subtractive. If you want, make a note here regarding this point. Make a note. In a transformer, the voltage per turn, the voltage per turn is remains same for all windings. Remains same for all windings. Okay, why it is, you will see in the EMF equation. So based on the given voltage rating, we calculated first EMF per turn or voltage per turn is 0.5. So same we applied for winding B, winding C. Then voltages we got. Then how much it is? So first, main flux direction. Based on the primary winding, current direction is this, and flux will be upward direction by right hand thumb rule. This is the flux direction, upward direction, same direction, continue. Okay, this is direction of flux, main flux, clockwise, based on the current we taken on primary side. Now, what should be the flux due to secondary winding and tertiary winding? Opposite. Now take the flux opposite here. Flux due to this winding is opposite direction. Flux due to this winding also opposite direction. Opposite to main flux. Now based on that flux you taken, apply right hand thumb rule. For winding B, the flux should be upward direction. So apply your 4 fingers there. So I'm getting current direction like this. So take little big diagram. Current direction I'm getting in this way. So with respect to B, it is going inside here and it is coming outside here. With respect to winding B, it is. Okay, all of you following, no? So take little big diagram. Okay, next, with respect to winding C, the flux should be opposite. That is from left to right it is. And if you apply right hand thumb rule, flux should be in the thumb direction. Then 4 fingers indicates current direction. Then if I indicate current direction, I'm getting like this. Check here. This is the current direction I'm getting by applying right hand thumb rule. Now here current is coming outside and it will go inside here. Now mark the polarities for B and C. Where is dot? Yes, current enters at a dot on primary here. So current should leave at dot in other windings. Leaving, here it is leaving. And for C, here it is leaving. Now this is plus, this is minus, this is plus, this is minus. Okay. Plus minus, plus minus. Now minus minus is joined. No, minus minus joined means what? Subtractive polarity. Then what is the magnitude of voltage? 50 minus 30. This is 20 volts. So the answer is 20 volts. Yes, most of you right. Yes, good. C polarity. What is C polarity? Flux is in this direction for C and current direction is 4 fingers. Apply your 4 fingers in the C winding. Then current is coming down now here. 4 fingers is coming down. So this is coming out. Current leaving. Current enters at dot on primary, current should leave at dot in all other windings. Where it is leaving? Here. That's why it is dot. Now dot, this is dot. Now which two are joined here? Undotted terminals are joined, means subtractive polarity. Then voltage will be 20 volts only. Same procedure if there is any number of windings. You need to mark the polarity and check for all other windings. Okay. See, that winding B and C, some people are asking, doubt is one of the student. B and C both we connected across X and Y. We need to add total turns. Yes, we need to add, but when it is, when there is no change in the sense of winding. But here sense of winding is different for B and C. If you observe the figure, for B, it is wound from top here. Okay, it is wound from top and proceed in this in this way. But for C winding, it is the sense of winding is checked. It is not from top started, it is started from bottom. That is, it is started from back side. Sense of winding is different, no, for B and C. That's why you should not take total turns. You should not take total turns. Otherwise, if you take total, 160 turns will come. So 160 into 0.5, 80 volts. No, because sense of winding is changed for some part of winding and other part of winding. For that reason, this polarities is considered. Okay. See what I said, current leaving is dot, and why I'm taking plus means I already said dot means plus, undot means minus. This is completely wrong. You can consider dot is negative, you can consider undot is positive. Anything you can take, but follow any one for all. That's why I taken dot is positive, undot means negative. Otherwise, you take dot means negative and undot means positive. Dot means negative, undot means positive. Anything, you will get same answer. Okay. Clear now, all of you? Next, one more question. Next question. EMF per turn, how to calculate? EMF per turn, how to calculate? See, 100 volts winding, 100 volts is applied to winding A. And how many turns are there in winding A? 200 turns is given. Winding A having 200 turns. 100 volts is applied. Then what is the voltage per turn? Total voltage is 100. Total turns is 200. 100 by 200, that is 1 by 2.5 volts. And it is same for all other windings. That is we applied here. Okay. Clear, Priyanka? Okay. Next question. It is little. Is the question visible to all of you? A little darkness is less. So try to read the question. See the question. The circuit diagram shows two windings lossless transformer with no leakage flux excited from a current source I of t. So here current source I of t and the signal is given. Okay. The transformer has magnetizing inductance. So this is mutual inductance only. This is mutual inductance. M given. Mutual inductance is given. Now first question is this. Second question is this. The peak voltage across A and B with S open. A and B means secondary side. Secondary side. What is the voltage on secondary side? Voltage on secondary. How to find EMF on secondary? E2 equal to what is the formula? So I given two formulas there previously. What is that? N d phi by dt. If there is flux signal and number of turns, use N d phi by dt. Otherwise, there is no number of turns and there is no flux relation. Then if current is there, what is the equation? M into di by dt. M into di by dt. So there is mutual inductance 400 by pi. M value given 400 by pi millihenry it is. That is important. 10 power minus 3 henries. And di by dt slope. That slope you can find here from the given signal. Di by dt, change in current with respect to time. Now observe, this is current variation I of t and this is time variation in millisecond. Okay. Now from 0 to 5, 0 to 5 I'm taking change in time and change in current di by dt. 0 to 5 I'm considering. In 0 to 5 millisecond, what is the change in current? See, this is 10 amperes. This is 10 amperes. In 0 to 5 millisecond, change in current is 10 amperes. So I'm directly applying here E2 equal to M value is 400 by pi into 10 power minus 3 into change in current. In 5 millisecond, change in current is 10 minus 0. And what is the time? 5 millisecond. 5 into 10 power minus 3 minus 0. In 5 millisecond, the change in current is 10 amperes. So slope is taken di by dt. Now solve this, you will get magnitude of voltage directly. So E2 equal to 400 by pi into 10 power minus 3 into 10 by 5 into 10 power minus 3. So this gets cancelled. 10 power minus 3 and this is 5 2. So directly 800 by pi volts. 800 by pi volts. This is magnitude of voltage on secondary side with respect to given current signal. 800 by pi, option D is right. This is first one, 800 by pi volts. Next, second. Read the second question. For second question, current signal is given, equation is given, current equation. Previously current signal we have, but now current equation we have. Same formula and again substitute here. Same equation, E2 equal to M into di by dt. Now M is 400 by pi into 10 power minus 3 because millihenry given it is. If you miss the 10 power minus 3, your answers will be wrong again. Into current equation is there, I of t equal to 10 sine 100 pi t. So d by dt of current signal. What is the current signal? 10 sine 100 pi t. This is current signal. Now differentiate that. What we need to find? The peak voltage across A and B is dash. Peak voltage or maximum voltage is how much? Maximum is how much? So if you calculate 400 by pi, 10 power minus 3, differentiate this equation. 10 is constant. Sine 100 pi t. What is sine omega t? Cos omega t. So cos 100 pi t with respect to t we are doing. So 100 pi we multiplied again. Now here 100, here 10, and 10 power minus 3 gets cancelled. So finally 400 by pi, pi also cancel. 400 cos 100 pi t. So finally you will get this equation. Now this is of the form Vm cos omega t. Okay. This equation is of the form some sinusoidal variation Vm cos omega t. Now what is the maximum value in this? Vm is the maximum. What is the question? Peak voltage is how much? That is maximum voltage. What is the maximum voltage? This 400 is the maximum voltage. So answer is 400 volts. Clear all of you? See, when AC is closed, then also same answer. There is no change. This is just wantedly given like switch open, switch closed. You consider t greater than 5 also anywhere, because slope will change now here, current variation. You can consider from 5 to 15 millisecond also. Anywhere, di by dt, change in for any time duration, you can consider that for any time duration. 5 to 15 millisecond for the same slope you have to take. But switch open condition, no, they asked. There is no use of that 30 ohms load. No, EMF induced in windings will not depend on load. Whether there is load or not, EMF will induce in the windings. That doesn't depends on load. EMF induced will depend only on the flux in transformer, and that flux in transformer depends on what? Current, primary current. If current is more flux will produce, more EMF will induce. If current is less flux, less EMF. Okay, we no need to consider load here. Switch closed or switch open, there is no use. You no need to consider that switch concept here. So you forget about the switch concept here. Remove this totally. Wantedly it is given. So some questions will create in gate like to confuse. There are so many questions like this. You no need to use this switch here. Wantedly it is mentioned just to confuse. Switch open, switch closed. Then people will think about switch only here, not actual concept. Okay. 1:1 transformer means what? Suppose you got the first question, E2 is 800 by pi. What is the primary voltage? Also same 800 by pi. Now secondary side maximum voltage is 400 in second question. And what is the primary voltage? 400 volts only maximum voltage. 1:1 means same voltages on primary and secondary. Okay. See here, try to understand I of t is not on secondary they given. They given I of t. Where I of t? Observe primary side it is. And why you taken that current and multiplied with this resistor 300 volts is drop. These are all not required. Current I of t is the primary current, not secondary current. Observe the figure. Okay, next question. See this question. Read the question. A magnetic circuit has 150 turns coil. So this question you can consider related to transformers or related to network theory. In network theory, in the magnetic circuits, we will get the questions like this only. Okay. The magnetic circuit has 150 turns coil. The cross-sectional area is 5 into 10 power minus 4 meters square, and the length of the magnetic circuit is this. What are the values of magnetic field intensity, that is H, magnetic field intensity, and relative permeability, mu r, relative permeability, when the current is I equal to 2 ampere and total flux is phi equal to 0.3 into 10 power minus 3 webers, and it is having number of turns 150, and area given, cross sectional area is 5 into 10 power minus 4 meters square, and length of the magnetic circuit also given 25 into 10 power minus 2 meters. So direct substitution in formulas. Direct substitution. See, what is H? Magnetic field intensity is what? H equal to mmf by length of the circuit. mmf by length. What is mmf? N into I, number of turns, and current divided by L, ampere turn per unit length. Ni, N is 150, current is 2 ampere, length of the magnetic circuit is 25 into 10 power minus 2. What is the answer? This is how much? 1200, right? 1200 ampere turn per meter. So magnetic field intensity. Next, second one is relative permeability. We need to calculate. Then what we need to apply? So we can apply the BH relation here. What is the relation between flux density and intensity? B equal to mu H. And from this equation, what is B again in terms of flux? Flux per area, nothing but flux density, equal to mu is mu naught into mu r into H. H we calculated now, directly you can substitute. Now only unknown in this equation is what? Mu r. Remaining all we have. Substitute. Substitute all the values. Phi is 0.3 into 10 power minus 3 divided by A, area of cross section is 5 into 10 power minus 4 equal to mu naught 4 pi into 10 power minus 7 into mu r we need to calculate, and H just now we calculated 1200. So only unknown here is mu r. How much it is? Mu r is how much? Yes, mu r is 398. Okay, the relative permeability is approximately 398 liter. So permeability is 398 and intensity is 1200. From given options, yes, option A is satisfied. Yes, right. Yes, right. This type of question given in engineering services, no, actually there without calculator we need to solve it. Is okay, difficult, but approximately the values whatever you are getting nearby, based on that you need to answer. And if you observe one thing here, 1200 you got first one. Okay, 1200 and relative permeability required. Okay, relative permeability we need. Now there is a flux 0.3 into 10 power minus 3. Some flux is there. Some flux is there. So flux is there means it is a good magnetic material only. Generally flux in milliwebers only. Flux is in milliwebers only in ferromagnetic materials. But if you observe the fourth option, 1200 and 500 into 10 power minus 6. That means this relative permeability is very less, no, less than 1 it is. Relative permeability is what? Very less. That means this is a diamagnetic material. Based on the given option, option D, it is not at all correct. So without solving that, once you know 1200, by observing option, you can put directly A it is. You no need to go for D also. That is, you no need to solve mu or completely here. Without calculator, this value you cannot solve. Okay, like that we need to put options in the engineering services particularly. Without calculator also, we should be able to answer for some questions. Okay. Completed. See this question. See this question. Read the question once. Read the question. Two single phase transformers with the turns ratio 1 and 2. First transformer 1:1. Second transformer 1:2. Okay. 1 and 2 respectively are connected to a three-phase supply on primary side as shown in the figure. See, there is a supply here between A and B. There is a supply here B and C. That's it. Now, what is the voltmeter reading here? Voltmeter reading. Now, 1:1 transformer means what? Whatever the voltage is there on primary, same voltage will be there on secondary side. Okay. Now, what happened here? This is 100 at an angle 0. Primary voltage. 100 at an angle 0. Then what is the secondary voltage? Same. Magnitude is same. But 180-degree phase shift will be there or not? Yes. 180-degree phase shift. Secondary voltage compared to primary voltage, 180-degree phase shift. In the same way, 1:2 it is. Then if primary voltage is 100, what is secondary voltage? 200. 1:2 it is. Step up. So 1:2 means step up. So secondary voltage will be 200 volts. Okay, because of 1:2 ratio. Previously 1:1 same. That's why 100 volts only taken. 100. But here 100, 200 because 1:2. At an angle already there is minus 120. Now one more minus 180 added. Total minus 300 degrees. Okay, 200 at an angle minus 300. Now what is the voltmeter reading? Don't add directly 100 plus 200. It is not arithmetic sum. It is vector addition you have to take. 100 at an angle minus 180 plus 200 at an angle minus 300. So take your calculator and in complex mode only do the sum. Do the sum. What is the answer? Yes, the sum of these two is what? 173.2 at an angle 90 degrees we get. So this is voltmeter reading, but voltmeter will not read these angles. It will read only the RMS value, no, MI instruments. So the answer is voltmeter will read only this magnitude 173.2 volts. Okay, you should not add both directly. It is not direct addition, vector addition. Yes, 173 volts. So generally it is lagging, no. That's why we are taking minus, not plus. secondary voltage lags the primary voltage by 180 degrees. So lead also you can take, but according to the definition, we are following this. 180 degrees secondary voltage is lagging. Without calculator, you can solve like, see, 1 at an angle 0. How can we write it is cos 0. What is A at an angle theta? First, in both rectangular form, A cos theta plus J A sin theta. Like this, you need to expand each one and then calculate the sum of these two. Okay, like that you can find without calculator. For small angles we can find, but for angles like 52 degrees, 56 degrees, we cannot calculate without calculator keys. Yes, RMS values. Okay. Anyhow, magnitude is same, no? Minus 90 or plus 90, magnitude you will get same. So with this, the introduction part we complete. Now we will start the construction part of transformer. About meters, you will get in measurements now, MI instruments, MC instruments. So where we use MI instrument for AC measurement, we use MI, and moving coil type for DC measurement, because it is AC, no? Whatever the meters we use here, MI instruments only, which measures RMS value. Let's see the construction part. Construction of transformer. Yes. See, mainly in construction part, whether it is GATE or ESC or any examination, we have only two parts. One is the transformer core and second is transformer winding. So that is only we are drawing every time, transformer core and transformer winding on that. That's it. But if you see actually uh, in transformer, outside transformers, can you see these two parts? You cannot see. Core you cannot see directly. Winding also cannot see directly. Not visible because that is inside the transformer. And outside what you can see? Only the tank we can see outside, and some other parts we can see. But the main two parts not at all visible for us. But only we are going to learn here about these two parts mainly. One is transformer core, transformer core, and second is transformer winding. So we are going to learn mainly about these two parts, transformer core and transformer winding. Okay, beside this, I will show you the complete transformer once, the outside parts, what are the uses and everything. Just briefly, I will give idea on this complete transformer. See the figure. See this. Considering a small transformer. So this is our transformer core and transformer winding. We are going to learn about these two only mainly here. And this complete transformer core and winding, where we place? We place it is in a transformer tank. We place in a transformer tank. This is our transformer tank. Okay, and it is completely filled with what? Oil inside. is completely filled with oil inside the transformer. This is our transformer oil. What is the use of the transformer oil? This is also one of the question in many examination. Transformer oil purpose. It provides cooling to transformer and also insulation to transformer. Cooling and insulation. It provides both cooling and insulation to transformer. Cooling, how it provide cooling? Yes. So we will see how it provide cooling and insulation. How it is providing insulation to transformer? Because when you touch the transformers outside, suppose the tank, let us touch the tank once. Do you get any shocks? No, mostly 99% we don't get any shocks if you touch the tank of the transformer, because the oil inside acting as a insulating medium between the transformer core winding and the outside tank. It is acting as insulation there. So like that, it is providing both cooling and insulation. How it is providing cooling, we will see again now. Now, this complete transformer core and winding placed in the transformer oil, and the windings we are taking outside. Observe here, this is high voltage winding, this is HV winding, this is LV winding, less number of turns. Now this HV winding is taken out through these bushings. Two bushings required, that is insulators. Two bushings we call. Through that inside we have a conductor in that insulator. It will come outside like this. Okay, bushings. Generally, the size of HV bushings you can observe in transformers also outside. Some bushings or insulators will be large size and some are small size. That small size bushings are LV bushings. LV bushings will be small size. HV bushings will be large size. Okay. Now at the top of this transformer, we are placing a conservator. So this is conservator tank. Okay, in between the transformer tank and conservator, we have Buchholz relay. In between the tank and conservator, in between these two, we have a Buchholz relay. So about this Buchholz relay, you will see clearly in the protection in the power system. Okay, maybe I think already you know about this Buchholz relay, how it protects. It protects the internal fault. It protects the transformer from internal faults. Okay. Now these are radiator tubes. These are radiator tubes we call. This is also for cooling purpose. Radiator tubes we provided for cooling purpose of transformer. And this is the outlet for transformer oil whenever it is required to change. And this is breather. This is breather. Now I will tell what is use of all this here. Listen. So many times in interviews of engineering services particularly, they ask about breather. They asked about breather in transformer, because most of the people will learn about transformer core and winding very clearly, but they don't know the outside parts clearly, and they don't have practical information also with them. Then how they can survive? Everything theoretically, how can we learn? You should know clearly about all the parts here. They are asking many times about breather. What is the purpose of breather? How it will function in transformers? So I will explain here clearly. Observance. See, the cooling can be provided. We have cooling, oil cooling or air cooling, and also gas cooling. We can provide cooling by oil, that is regularly we are using, and air also we use. Some air we will circulate in that inside. Air will circulate, how it is we will see now. And gas. So gas means you can provide that gas cooling only by side walls. Gas, you can send continuously the gas onto the surface of the tank. It will absorb the heat from the tank, so that some cooling is provided to that. And one more, by using fans, just like exhaust fan, however we use in our kitchens. Here also you can provide that exhaust fans here, or cooling fans we call. The fans, some transformers will have at the side by we provide these fans to take the heat continuously from the tank, and at some of the transformers we also place the cooling fans at the bottom of transformer, bottom, to take the heat continuously outside. Cooling is very very important, not only for transformer, that may be generator, that may be motor. Cooling is very very important. If you don't provide cooling, automatically the generators or maybe transformers, anything, definitely they will damage first. Why? Heat. Why heat is producing? Yes, main two losses: iron loss, copper loss. Whenever heat continuously increasing, no, which one will damage first? Copper wires will damage first. So once they burn, then nothing they can supply. So cooling is very very important in generating plants also, you know very well. Power plants, cooling is very important. Now, in every transformer we have this radiator tubes, or we also call radiator fins. Maybe in some transformers you have observed it is not like a tube, it is not like a pipes, it is like small thin plates, like thin plates will be there side by side with some width. Radiator fins we call. Number of fins will be there, and in between some gaps will be there. That is to circulate air through that, so that oil gets cooled. Okay, different types of cooling methods. And on the nameplate of these transformers, if you observe, the type of cooling is ONAN, oil natural, air natural. Oil cooling is there, and air natural. Air cooling is outside air will touch that radiator fins or tubes, and it will also provide some additional cooling. So this term you will see on the nameplate of transformers. Type of cooling will be ONAN. ONAN means oil natural, air natural. Okay, it will be there on that. This is about cooling. Now observe here. What is the purpose of this conservator? Conservator. So if you observe, actual conservator will be like this. The conservator will be like this at the top of the transformer. Like this, it will be located. And exactly at the center of this conservator, you can see one small mirror here. Okay, this is connected to transformer tank inside. Here, this is mirror. A small mirror is located, and here also we have some oil, but the oil is not completely filled in this. There is some gap here. Completely we won't fill the conservator with oil. Little bit gap will be there. What is the purpose of that? We will see now. This is mirror. What is the purpose of conservator? Mainly, the purpose of conservator is mainly to check oil levels. To check oil levels. Why we need to check oil level? Yes, oil should be there almost the same in order to provide better cooling to transformer. Otherwise, if oil level is reducing, no, why oil level will reduce? Yes, if aging of transformers increasing continuously, they are in operation after 1 year, or after 2 years, or after 6 months duration, the oil levels little reduce. The oil levels little reduce. Now, whenever oil level is reducing, cooling capacity also reduced. Then losses increase in transformer. So for that reason, oil levels regularly we need to check. And that oil level we will check just from this mirror. Just from the mirror. Because just like our water tanks, can we check the oil level in transformer every time by opening the top of the tank? No, we cannot open like this. The top of this tank, can you open? We cannot open this. That is the reason freely or easily we can check the oil level using this conservator. If oil level is reducing here, means the oil level in transformer also getting reduced. Then we will refill again some more oil in that. Generally, this transformer oil for every 2 years or 3 years, based on the operation of the transformer, we will refill, so that better cooling and insulation it will provide. Okay. Now, this is the purpose of conservator mainly. And from the conservator, from the same conservator, it is connected to a breather here. This is breather. It is connected to a breather. 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 Very, very important. See the function. See, this is the actual figure. It is connected to a breather here. This is breather. Now see what is the purpose of breather. I will show you the breather diagram separately now. Observe this. This is breather. Breather. Conservator is there here. At the top, conservator is there. From the conservator, there is a link to this. Is connected here. Conservator. Okay. Observe. However we breathe, however we are breathing, in the same way, transformer also will breathe. Do you know? Transformer also will breathe, but not like us quickly. Slowly it will breathe. It will take breathe inside. It will take, that is, it will give breathe outside. Breathe in will be there and breathe out also will be there. Just like however we are breathing, taking breath inside and leaving outside, in the same way, transformers also will breathe here. See how it is interesting. Observe. There is a small level now here, that is in the conservator some gap is there. Check, there is some gap in the conservator, completely not filled by oil. Some gap is there, some gap is left wantedly. Now what happened, this gap is, see, whenever we operate transformers, whenever we operate these transformers at full load conditions, so generally there is a 10 kVA transformer. So for example, what is the meaning of the 10 kVA on the nameplate? On the nameplate, capacity of transformer given 10 means what? This transformer capacity 10 means you can connect a load of 1 kVA, you can connect a load of 2 kVA, and so on. You can connect up to 10 kVA. That is the capacity. 15 kVA you should not connect because capacity is 10 only. It will become overload. You should not connect. So 1 to 10 kVA, any load you can connect. Now observe, whenever the load is increasing, currents increasing or not? Yes, currents increasing. Mainly we have two losses. What are the losses mainly in every machine? Iron loss, copper loss. Iron is in core, that is the core of the transformer here, and copper loss will take place in windings due to currents in windings. So that everyone knows. So iron loss is taking place, copper loss also taking place. Whenever load increases, current in windings increase. So losses in transformer increases. Losses in what form? We are getting losses in the form of heat. Heat only the losses in every machine, that may be transformer or rotating machines. So whenever losses increase, heat increase. Then if load increase, losses increase, still heat increases. Heat increases. Whenever heat increase, the oil gets heated up or not? Yes, the oil also gets heated up. Whenever oil gets heated up, the oil level little increases or not? Yes, the oil now little expands. At high temperatures, the oil little expands. The oil little expands. Whenever oil little expands, this gap will reduce or not? Yes, the gap will little reduce. The gap little reduces. Okay, up to here it will be there. The gap little reduce. Whenever gap little reduce, previously there is more gap, means more air is there in that. But once oil level increase, the gap is reduced, means that air will come outside or not? Yes, whatever the air is present previously here, that air will come outside through this breather. This is called breathe out process. This is breathe out. So when transformer is breathe out, when load is increasing or load is decreasing, whenever load increases or at high load condition, high load conditions, because heat is more. As load increasing, transformer will breathe out. So breathe out. Now that air, so tell me, whatever air is present here, that air is having some heat or not? Yes, that air is having some heat, because that oil heated up, total heat will be there here itself, means that hot air it is. Now that hot air is going outside through this breather. Means it is providing cooling or not? Yes. Hot air is going outside, providing some cooling through breather. Next, let us reduce load on transformer. When load reduce, what is the losses in transformer? Reduces. When losses reduce, heat also reduces. Now, whenever heat reduce, the oil heat also reduces. Then oil level, previously oil is what? Expanded. Now the oil gets contract. The oil gets contract means oil level little reduce. Whenever oil level little reduce in conservator, here gap will increase or not? Yes, this gap will increases. Now whenever gap is increasing means there some air is getting sucked or not? Yes, suction process will take place. Some air will enter there. How that air will enter? That air will enter from breather only. That air will enter from breather only. Now people will get doubt. If there is no breather here, then also it will take space. Yes, remove the breather here. Just put a small pipe here from conservator. Now it will breathe in and breathe out or not? Yes, it will breathe in and breathe out. But without breather, if it is taking place, there is a problem to transformer. See what it is. Observe here. During breathe out process, air is coming outside now. The hot air is coming outside from transformer. So this is not a problem. Okay, no need of breather here. But during breathe in of transformer, breathe in, air is going inside the transformer from outside. The outside air is going inside the transformer. Air is going inside. Now, whenever air is going inside the transformer, outside air, is it the pure air? So whatever outside we are taking the oxygen, whatever, is it the pure oxygen? No, it is polluted. No, yes, definitely it is polluted. Whatever the air is there outside, polluted. Dust particles will be there, and some moisture content will be there in the air. So this air, if directly enters into transformer, no, without this breather, if it is directly enters, there is some problem to the transformer oil and transformer core and transformer winding. So the properties of that oil gets reduced because of that polluted air is going, dust particles is going inside. So it will damage the transformer inside if air is going directly without breather. That's why we placed a breather here. See now, breathe out process, no problem. Same, during the breathe out process, the air will come outside. Air will come outside through breather, and from this small gap hole, it will come outside. See, actually, this is the bottom hole of breather, and it is connected to a oil cup here. There is a small oil cup attached with this cap. So this is open. Air will come outside. Air will go out inside, and still it is connected with a small oil cup. A small cup filled with some little oil. So what is the need? I will tell you. And this complete breather is filled with silica gel. Silica gel is filled in this, and actual the color of this silica gel is what? This one, blue color, light blue color. The original color of silica gel is light blue, means that is the best one. Otherwise, once it is getting pink color now, means the capacity of that gel is reduced or strength of the gel is reduced. Actually, what silica gel is doing? The silica gel, what it is doing is, whenever air is going inside, in the air we have moisture content mainly. That moisture content present in the air is absorbed by silica gel. The moisture content or moisture present in the outside air is absorbed by silica gel. Now it will absorb here. Then whatever air is entering into the conservator, that is the pure air. There is no moisture content in that. So that is main purpose of silica gel. Whenever air is going inside, it will absorb moisture. Now what is the purpose of this oil cup here? Yes, in the outside air, we have dust particles. Small, very fine dust particles will be there. Now once you place, this is the, observe, this is small hole to the breather. If it is directly open, no, dust particles directly enter into this. If the if that hole is directly open, dust particles directly enters into this. But what we are doing is that hole we will place in a small oil cup. In a small oil cup, it is immersed. Now what happened? Whatever outside air is entering, it will touch the oil first. The outside air will touch the oil first, and whatever the dust particles is there, the oil will absorb that dust particles there itself. Now, without dust particles, the air will enter into the breather, and whatever moisture is present, that is absorbed by this silica gel and then enters into the conservator. Like this, breathe in process is taking place. Breathe in and breathe out. So when breathe in process, whenever load increasing or decreasing, whenever load is decreasing, whenever load decreases, breathe in process. Whenever load increases, breathe out process. Load increase, losses increase, heat increase, oil expand, air will come outside. That is breathe out. Breathe in, load decreases. Okay, clear all of you this about conservator and silica gel. Breather. See, once silica gel is converted into pink color, actually it is blue color, bluish color, light bluish color at the original condition. But when it is absorbing moisture content, no, the color will change. So once it converted into pink color means you need to change because there is no capacity to absorb moisture. Once it is pink color means there is no capacity to absorb moisture content in that. We need to change the silica gel. Clear all of you this one? What is the mirror purpose? Just now I said now with from the mirror only we are checking oil levels there. Oil level in conservator from the mirror we will check. No need to open tank anything. Bushing is nothing but insulator because the outside inside winding two terminals, LV2 terminals, HV2 terminals. The two terminals we need to take outside the tank now. How can we take directly? There we will place insulators or bushings we call. So in that through that bushings we will take that wire outside, not directly. So gap is there in conservator. Why there is a gap in conservator? Just now I said gap is required because if you completely fill, whenever oil gets heated up, it will expand. Then is there any gap to expand the oil? No. Then there will be a problem because overheated, there is no oil gap to expand. Then there it will get problem to either transformer winding mainly and buckles relay will operate unnecessarily for this reason. So small gap we create. Because of that small gap we placed, hot air is going outside. It is one way of cooling providing. Hot air is going outside. So cooling provided. Whenever breathe in process is taking place, outside air is entering into the conservator or transformer. So outside air is cooler than inside air. It is also providing cooling. By using breather, we are also providing cooling. Okay. Radiator tube, nothing is there. Oil is circulating in the tubes. Oil is circulating slowly, not very highly. Whenever oil getting expanding and contract, the oil slowly circulates in the radiator tubes. Whenever oil circulating, no, the surface, the radiator tubes will contact with outside air, so it will provide little cooling. Oil will circulate in that. Outlet is for oil, taking oil outside. Yes, however, oil color will change. Why? You take engine oils in bikes also. What is the actual engine oil color? Little reddish color will be there at the starting, new one. But after 6 months or 1 year, if you use continuously, what happens to that oil? Very, very black color. So oil colors will definitely will change. Transformer oil color also will change. Fins is same as radiator tubes, but they are not like tube or pipe. They are like plates. They are called fins. Maybe you have seen so many where in transformers. Okay. Transformer oil only. There is no any specific name for that. We call transformer oil only. Yes, transformer oil only it is. With a good dielectric strength property. And no need oil gets old means how can we know? So very simple. If it is in continuous operation for 1 year, because that people will know that this transformer oil capacity will be 2 years or 3 years. So within that duration, they will change. Okay. Generally, if you observe the outside distribution transformers, very rarely they will change the oil in that. Very rarely. Suppose whenever there is fault occurred in transformer, then only they will take it is for service. Up to that, no one will change the transformer. Maybe you observed in your areas also. Transformer oil regularly they never change. Once there is a fault in that, then only they will take the transformer to service. There they will change the oil if required. Okay. In the radiator tube, that oil is circulating, no? Slowly. When oil is circulating, what happened? Oil inside transformer very heat is more, but radiator tube having more surface contact with air throughout that tube, then it will provide some cooling, no? Like that. That depends on fault condition, internal fault or external fault. No, silica gel when we require to change, simple, no? Just observe the color. If the color is completely changed to pink color without having any blue particles in that, if completely pink, then we need to change. Okay. So okay, this is the complete details of other parts of transformer. So let's continue the actual first transformer core. Shall we take break, and after break we start? Okay. Okay. So take break for 15 minutes. After that we start transformer core, first one. Okay, so see the first one, transformer core. First part of transformer construction is transformer core. So what is the main purpose of this core in transformer? So core is very important here because in the definition we have seen the power is transferred from one winding to other winding or from primary to secondary through what it is transferring, through this core only power is transferring, or through magnetic circuit. This core we also call magnetic circuit. Okay, so first of all the power is transferring from primary to secondary through this core only. So it should have very good properties, like what is flowing in the core here, mainly flux is passing through the core. So whenever flux is passing through the core, it should have good magnetic properties or not? Yes, it should have good magnetic properties. Like what are the properties? Let's see. So flux is passing through this. So power is transferring from one circuit to other circuit through this core only. For that reason, the transformer core should have high permeability. So when flux is more in the core, if the permeability is high, so the transformer core should have high permeability. Okay, high permeability. So it is indicated by mu. Next, second. So when flux will pass easily in the core, so whenever the reluctance of the core is less, just like current, when current will pass, high current will pass in the circuit. If resistance of the circuit is less, high currents can flow easily. So it should have low reluctance. The transformer core should have low reluctance. Low reluctance, just like high conductivity in electric circuits we call high conductivity and low resistance. In the same way, these two properties in magnetic circuits, high permeability, low reluctance, and it should be a ferromagnetic material. Again, in magnetic materials we have three types: diamagnetic, paramagnetic, like this. So it should be a ferromagnetic material. The transformer core should be a ferromagnetic material. And one more is, this is a iron or core. Whenever flux is passing through this, some losses will take place. They are hysteresis loss and eddy current loss. Totally we call iron loss it is. And that iron loss in the core should be as much as possible less. So it should have low iron loss. It should have low iron loss. So you write simultaneously. The transformer core should have these properties. The transformer core should have these properties. First, high permeability, low reluctance. It should be a ferromagnetic material. And fourth, it should have low iron loss. It should have low iron loss. Okay. Now, if you fetch for material, which material will have these properties? Tell me, which material will have these properties? So these properties are there in silicon steel. These properties we have in silicon steel. That's why majority of these machines, 90%, whatever we have, transformer, induction machine, synchronous, DC machine, mostly silicon steel only. Mostly. So very easily you can remember regarding material. See, transformer core, silicon steel; induction machine, silicon steel, stator, rotor; synchronous machine, stator, rotor, silicon steel. But only in DC machine, the material will change. Only in DC machine, the stator of DC machine is made up of cast iron, also called cast iron or cast steel it is. Only for DC machine, the Stator of DC machine is made up of either cast iron or cast steel. Only stator. And rotor of DC machine also silicon steel. Okay, you no need to remember or no need to confuse regarding material. Every part of machine is silicon steel except stator of DC machine, and remaining all silicon steel only, no doubt. Okay, now first of all, what is these materials? See briefly once. First, iron. What is the indication of this chemical name? Ferrous, Fe. Iron is indicated with Fe, no? Iron it is. Now, what is steel? How can we made a steel? What is the composition of steel? Iron plus a small amount of carbon. Iron plus small amount of carbon will become steel material. We call it is steel. Now, what is silicon steel here? Silicon steel, nothing but to the steel, but that is combination of iron and carbon. To the steel, we add a small amount of silicon plus steel. A small amount of silicon is adding to the steel. Then that material we call silicon steel. And how much percentage of carbon? If you talk about material little, the percentage of carbon is very, very small. See, total iron 100%, for example. And now 98% is iron, 2% is carbon. 2% is carbon. Now, what is cast steel here? Cast steel. In cast steel, the same iron will be there plus carbon will be there, but the percentage of carbon is more in this, like 3%, 3.5%, 4% will be there. So more percentage of carbon in case of cast steel, and in normal steel we use less percentage of carbon, less than 2% mostly we use. Small percentage of carbon we add to the steel, we add to the iron, we call it is a steel material. Steel is strong compared to iron. And silicon steel, silicon is added to the steel. Silicon steel. So silicon steel we are using mostly for every machine except stator of DC machine. Why it is? You will see there in the stator of DC machine. Why we are not using silicon steel there? Not required. Why it is? You will see. Now, so these properties are there in silicon steel. That's why we prefer silicon steel. But particularly for transformer, we are going with one more material. Maybe all of you know that material also, CRGO steel. Now, one important question here is CRGO steel and silicon steel same materials or different materials? CRGO steel and silicon steel, because people don't know, most of the people think that CRGO steel, silicon steel, these two are different or same? These two materials are same or different? Yes, these two are same. Yes, good. These two are same. CRGO is also silicon steel, but there is a slight difference in that. Material is same, no doubt. Material is same, silicon steel only. CRGO also silicon steel. But why we call it is CRGO? And what is normal silicon steel? Now we will see here. So first of all these properties are there in silicon steel. So we prefer silicon steel only. But still, in normal silicon steel, we have a small minor problem. Due to that, we are going with CRGO steel. So what is that is? Observe now. In case of normal silicon steel, now if you take a small piece of silicon steel, let's consider a small piece of silicon steel. Okay, small piece is taken. Now in that silicon steel, what is the shape of that silicon steel? First, shape means don't tell rectangle or square or circle like this. Shape of material I'm not asking. Shape of silicon steel, crystalline structures. Maybe in your engineering physics in the colleges, you have one subject like applied physics or engineering physics like this. So there you will learn about crystalline structure of materials. Like we have BCC, body centered cubic structure, or face centered cubic structure, like this lattice structures. So in that way, if you talk, the shape of the silicon steel is called BCC, body centered cubic structure. The shape of the steel is BCC, body centered cubic structure, like this. BCC, body centered cubic structure. Actually, these shapes we cannot see with our naked eye. Physically, we cannot see these shapes because these are all microscopic pictures. BCC means body centered cubic structure, like this. So if you observe microscopic picture of that small silicon steel, now this is we call one cube I drawn here. This is we call cube, or you can in the material language here we call it is grain. Grain we call. So this is one cube or one grain it is. Like this type of grains in a small piece of silicon steel, lakhs of grains will be there. We cannot see that. Physically, we cannot see that. These are all microscopic pictures only. So if you draw here, there are lakhs of grains, but I am considering some few grains to show. In normal silicon steel, the grains are like this. So this is one grain, like this will be there. Okay, like this. Now in normal silicon steel, this is the microscopic picture of these grains. Is there any shape or any order of these grains? No. One is in this way, one is in some other direction, like the different orientation we have. This is called non-oriented steel. Normal silicon steel is a non-oriented. Oriented means what? One direction or one shape, but here no orientation. That's why we call it is a non-oriented steel. So normal silicon steel is a non-oriented. So what is the problem of this steel? Yes, there is a small problem here. What is that is? Observe the grain here. Observe this grain. In this cube or grain, these are all edges. These are all what? Cube edges. These are all edges of the cube. Total how many edges we have? Edge. How many edges we have? So totally 12 edges we have. Okay, these are all edges. Total 12 edges are there. And how many diagonals will be there in cube? Diagonal from one corner to other corner. See, top to bottom, top to bottom. So totally 4 diagonals we have. This is diagonal. Let's consider this is one diagonal. This is the path from one corner to other corner. Now let us allow flux pass. Flux is passing from this corner to. So I applied flux here and I need flux at this corner. Flux I want at this corner. Then what is the path of flux? Path. Which path flux will prefer? So we know very well. Flux always prefers to flow through low reluctance always. Now, if you observe edge and diagonal, where we have air gap, edge along the edge there is material, but along this diagonal we have a small air gap. So you cannot see actually in material, you cannot see all this. Very fine gaps will be there. So along the diagonal path we have small air gaps. Small air gaps is there. Now, is the flux will prefer to this? No. Flux prefers to flow through edges only. Now, how from this flux is preferred? Edge, any one edge. Suppose I am taking like this. This is one edge. This is next edge. Next, this is. Now, this is the path of flux. Okay. From this corner to this corner, flux is traveling like this. Why? It is fetching for low reluctance here. It won't take diagonal because diagonal offers high reluctance due to small gaps here. Now, come to the material. Now, if you allow flux here, flux is entered in this point. Now, in order to flow the flux through the material, now flux enters here. Now, these are the edges. Now, flux prefers to flow through edges like this, like this. Now, flux is fetching for low reluctance. So, this is the path of flux. Okay. This is the path of flux inside the material. Then, length of material is only this much. But what is the length flux is traveling? More, because of it is fetching for low reluctance through edges only. Because of non-orientation, the length is increased. Therefore, the overall reluctance of silicon steel is little higher. Little higher compared to other material, it is less. I'm considering about silicon, normal silicon steel and CRGO silicon steel. So reluctance is little higher here. So due to that little higher reluctance, magnitude of flux little reduce. Okay. So due to this problem, now what we do? So we have one process in mechanical engineering. We have rolling process. We have two process: cold rolling process, hot rolling process. Now what we required? We required orientation of these grains, because whenever the grains are oriented, now flux can travel easily through the edges. It no need to fetch because orientation is there. Length reduces, then automatically reluctance reduce, magnitude of flux increase. So for that reason, we are going to one mechanical process called cold rolling process. Cold rolling process. So simple process it is. Cold rolling generally we do in the range of approximately 70 degrees centigrade, 80 degrees centigrade, in this range. Hot rolling is there. Hot rolling very high temperature, 900 degrees, 1000 degrees centigrade. In that at high temperatures we do hot rolling process. But what we want, orientation we want. With hot rolling, you don't get orientation. Shape of material also will change. With hot rolling, is we don't do. With cold rolling, we will achieve whatever we want. For that reason, cold rolling we are going. Now, what is cold rolling we are doing in cold rolling? Simple. Like two rollers we have, two rollers, and these rollers is operated with high capacity motors in opposite direction at a low speed. Now we will insert the silicon steel material here. Silicon steel, normal silicon steel we insert here under these rollers at this temperature. At this temperature. So once it is rolled, so you will get the output now here. So if you insert this silicon steel piece between the rollers, you will get the material here. So you will get one material outside, and if you observe the outside material now after the rollers, and if you take the microscopic picture, you can see that all the grains in this will become oriented. All the grains are oriented in this. Because of this reason, this steel we call CRGO steel. So what is CRGO means? Cold rolled grain oriented steel. Grains are oriented now here. Because of what process grains are oriented? Cold rolling process. That's why we call simply CRGO steel. So this is a silicon steel or not? Yes, silicon only, but oriented. Silicon oriented steel. But what is normal silicon steel? Non-oriented steel it is. Normal silicon steel is a non-oriented, but CRGO steel is a silicon steel oriented. So this is also silicon steel, but oriented it is. Now what is the advantage of orientation? See, whenever flux is entered, as all grains are oriented, no, then edges are exactly coming in straight line, then easily flux will travel here. Then what is the length the flux is passing? Less. So automatically reluctance reduce. Magnitude of flux little increases. So which is better material now? Silicon or CRGO? CRGO. That's why we preferred CRGO for transformers only. This is also one important question. Only in transformer we are using CRGO. Then if you go to induction machine or any other synchronous machine, there we say only silicon steel. CRGO we never talk there. CRGO we never talk. And why we are not using that CRGO steel in case of rotating machines? If we use there also, flux will increase, no? Then why we are not using? Yes, there are two reasons here. There are two reasons why we are not using CRGO steel other than transformers. One reason is in all rotating machines, we have small air gaps. Okay, we have small air gap between stator and the rotor structures. So even if we use, suppose induction machine take, same principle, whatever transformer is there, induction motor also same. Now whenever flux is passing from stator to rotor, just like primary to secondary flux is going now in transformer, In same way, in induction motors also, flux will come from stator to rotor. Okay. Now, whenever it is coming from stator to rotor, it has to cross this air gap. It has to cross that air gap. Now, what that air gap will do? It will offer high reluctance to the flux or not? Yes, it will offer high reluctance. And due to that reason, little flux will change or not? Yes, reduces. Now, let us use CRGO strip because it is very low reluctance. Yes, use CRGO. Even if we use CRGO, there is a air gap in this or not? Yes. From primary to secondary or stator to rotor, there is a presence of gap. Can you avoid that gap? Can you make that gap zero? If it is zero, it is not rotating. So rotating machine is there must be air gap. So because of this reason, even if we use CRGO steel, air gaps will offer high reluctance. So there is no better use of using CRGO steel. But what is the drawback if we use CRGO? Generally, when we use anything now, advantages should be more compared to disadvantage. But here, advantage is less, disadvantage is more. What type of disadvantage? Cost will increases. If we use CRGO here in place of silicon steel, cost increase because of this additional process we are doing on that cold rolling. Cost of steel increase. Then what you are getting? Flux little increase, but not very high because of this air gap presence. So no use of using CRGO steel. This is one reason. And other reason is in transformer, the core is like this. Okay, core is like this. If grains are oriented, see these are grains in core like this. So along the path, along the flux path, if grains are oriented, there is advantage to flux, magnitude of flux increase because flux will pass through the grains like this only. Throughout the core, flux is passing through the edges. So there is use. But observe rotating machines, cylindrical shape, not like this, cylindrical shape. No. Now, if grains are oriented also, there is a difficulty in this because whenever flux is flowing, the edges cannot be in a straight line. The edges cannot be in a straight line. So even if we use CRGO steel, the flux will get difficulty while passing through the edges because it is not having aligning. It is cylindrical shape. So it is difficulty for flux passing through the edges, even if we use CRGO steel here. That's why there is no use of using CRGO steel in rotating machine. So in all rotating machine, induction machine, synchronous, we use only silicon steel. We don't use CRGO steel. Clear? So write one statement regarding this silicon steel and CRGO steel. Write the statement. In normal silicon steel, the grains are non-oriented. The grains are non-oriented. Due to this, the overall reluctance slightly increases. The overall reluctance slightly increases. Hence, the silicon steel is taken into cold rolling process where the grains will be oriented, where the grains will be oriented, which causes which causes low reluctance, low reluctance compared to non-oriented silicon steel, compared to non-oriented silicon steel. Hence, hence CRGO is preferred in transformers. CRGO is preferred in transformers. Okay, CRGO is preferred in transformers. So make a note below this. Make a note. Right. In all other rotating machines, write your one. In all other rotating machines, in all other rotating machines, due to presence of air gap, due to presence of air gap, the reluctance offered, the reluctance offered to the flux is high. The reluctance offered to the flux is high. Hence, there is no use of CRGO steel. There is no use of CRGO steel. Hence, a normal silicon steel is preferred. Hence, a normal silicon steel is preferred to reduce cost of machine. To reduce cost of machine. Okay, so this is about material. So just we have talked about material here. Silicon steel and CRGO steel we are using to reduce the problem of silicon steel. Okay, now let's see what type of core we have to choose, solid or laminated. What type of core we have to use, solid or laminated? Which one? Which core we have to take, solid core or laminated core? Everyone will tell laminated. Yes, right. Okay, enough. Yes, laminated. What is the need of lamination? To reduce eddy current loss. Yes, no doubt. Right only. To reduce eddy current loss in transformers, we are using a laminated core, but not solid core. So let us consider a solid core first. Solid. This core is solid. Now, when the core is solid, no, I'm not drawing complete winding here, just showing directly flux in this. Flux is passing through the core. Now, what happened here? Whenever flux is passing, what is the nature of flux passing through the core? Alternating only, time variable flux, time variant flux. So solid core it is. First we taken solid core. Solid core, this single iron piece, big one. Solid core having more cross section, surface area, more surface area for this. Now whenever flux is passing through this, what happened? Eddy currents will flow. How eddy currents will flow? Important. Eddy current. Now one more question is, why we call eddy current it is? Why we call eddy current? See, whenever there is a flux, a small amount of currents will circulate in the core. A current will circulate in the core body itself. This is called circulating current. Particularly here we call it is eddy current. Okay, particularly we call eddy current it is. Why we call eddy current it is? Why we call eddy current? Any reason? Hmm. Okay, so it is okay. Due to these currents, heat is producing and this is looks like circulating or whirlpool. Okay, everything is right, but why we call eddy current? Why it is given as name eddy? Why we call it is eddy current? Eddy currents create all negative things. Okay, yes. Eddy means constant. Okay, one of you given, right? Hmm. Yes, right. So simple. These currents looks like eddies in water. Eddies. What is that? So if you take a small uh, river or pond, that is standstill water, a small tank also you can take. So if you throw a small stone in that, no, so you'll get circular waves. Circular waves. What is that we call? We call they are eddies. We call eddies, that is, or simply eddies in water. That is we call eddies in water. That circular waves, whatever constantly coming, that is called eddies in water. In the same way, however, that eddies in water we are getting circularly. In the same way, these currents also will circulate in the core. That's why they call these currents we call eddy currents, or you can call circulating currents, or here particularly we name it is as eddy currents. It looks like eddies in water, but can you see that eddies in core here? No, you cannot see. You cannot see, but it is circulating in the core itself. So this is called eddy currents. Now, when there is a flow of current, let IE, to the flow of these eddy currents, some resistance offered by the core. Every body will have some resistance. Now, core or irons, silicon, steel, also having some resistance. Now, resistance offered by the core is RC. Now, immediately I square R loss will take place. This is called eddy current loss. This is called eddy current loss. What is eddy current loss? It is an I square R loss. Just like copper loss takes place in winding, in the same way I square R loss here. In the core it is due to the circulating currents or eddy currents. So this eddy current loss is in the form of heat. Due to this, the transformer core additionally heated up. Heat will develop. So why it is forming here? Just like Faraday's law is satisfying here. What is Faraday's law? Faraday's law. Conductor cuts the flux, or flux cuts the conductor. What is conductor here? The core itself conductor. Why? It is having some conductivity or not? Is it insulator? Insulator zero conductivity, but it is not insulator, no. Silicon steel. So there is some conductivity to this sigma. So flux is flowing in this. What is the nature of that flux? Maybe core is stationary, flux is moving in that. So variation is there. Immediately some EMF induced inside the body, EMF induced, and due to that EMF, currents will flow, and due to that current, loss will taking place. Loss is taking place. That is we call eddy current loss finally. Now, how to reduce that eddy current loss? So to reduce that eddy current loss, we should not use solid core. Now that solid core we have to make a laminated core. The solid core should be laminated. So we don't use a single big solid iron structure. We use a number of thin plates. A number of thin plates we use like this. But still in the figure, there is a slight deviation you may observe like this. Still it is not clear because this is just front view of the core I am showing. How it looks like. The same core, see, So it looks like a core is taken, normal solid core, and let's make laminations here. Like this, it is looking, no, this one. It is a laminated core. It looks like this, but actually, laminations we don't make in the front view. Laminations are not in the front view. If you see the front view of the core, you cannot see laminations. Side view only you have to see in order to observe laminations in it. So I will show you that clearly now. Observe in the diagram. See, this is our actual laminated core. Side view it is. If you see front view, no, you cannot see laminations. This is side view. Here you have laminations like this. Means a single solid iron we will cut into number of plates, number of thin plates, and each one we call lamination there. One lamination. Like that, all laminations we will attach together. Then completely it is a laminated core. Okay, this is laminated core having number of laminations attached or number of plates attached together. Okay, so whenever it is solid, no, if the core is solid, more surface area available. Now currents are circulating in this, eddy currents are circulating. Magnitude of current is more because current always depends on area of cross section. More cross section, more currents will circulate, magnitude will increase. So in order to reduce that eddy current loss, you need to reduce the magnitude of eddy current. How can we reduce that magnitude of eddy current? Just by reducing the cross sectional area available. For that reason, solid core is made into number of plates like this, number of plates. Then what is the in between each plate? See, this is solid core. Simple one small iron piece I am taking, and this is I am laminating now like this. I will cut into number of plates, just like you take a full bread, full piece of bread without slice, without pieces in that full piece, and then cut it is into number of pieces, and place jam in between each piece, and then attach together all. That is a laminated body. In the same way, it is cut into number of plates, and in between each plate I am considering insulation. See, this red lines indicates insulation. Insulation between two plates. See, this is one plate, this is one iron plate, this is one iron plate, and so on. These are all laminations we have, single lamination, and in between two lamination we have insulating material. Now what happened due to this? Current will circulate. You cannot eliminate this. You cannot eliminate. Current will circulate, but current can circulate only in this area. It cannot circulate totally because insulation is there here. Current cannot flow in that. So magnitude of eddy currents little reduces here when compared to this solid core. Magnitude is very high in solid, but in laminations, magnitude of current reduce. So the I square R loss also reduce. Eddy current loss is reduced. But if you face any question, how can you eliminate eddy current loss? So don't say blindly by laminations, because I am also one of the victim for this. In one of the interview, I faced this question directly. How can you eliminate eddy current loss? Because we cannot think in that way there. Immediately it will come by laminating the core. Because we know very well, no? How can you eliminate eddy current loss, they asked. So I also said by laminating the core. Again, they asked second time. Can you eliminate by laminating? I said yes. But answer is what wrong it is. But anyhow, they don't see that much there. They will check your facing interview at the same time to responding to the question immediately, because nobody can think like that. No, they are asking to eliminate or to reduce. We can reduce only, but we cannot eliminate this. We cannot eliminate eddy current loss. Eliminating eddy current loss means what? Eddy current is zero. Can you make eddy current zero? Never. We cannot make eddy current zero. If you want to make eddy current zero, total insulation you have to place. Then is the flux will go in that? No. So for this reason, we can reduce the eddy current loss by laminating the core. And one more interview question one of the student faced is they given a small iron piece, small silicon steel, small piece is given and asked to show iron loss in that. They given a small piece of steel, asked show iron loss in that material. How can you show? How can we show iron loss in this? Can we show any microscopic picture? Nothing. Then how can we show iron loss in this? Yes, you have to respond quickly, but it should come. How can we show? Iron loss you need to show means heat in that iron you have to show. Means you need to generate heat in that small silicon strip or small piece of iron. How can you generate heat? Then don't rub it is on the floor and don't give it heat is produced. Not like that. However, in machines heat is taking place. In the same way you have to produce heat in that. Very simple small experiment you can do for this also. What is that? Very simple. So take a small permanent magnet also. So how can you generate that eddy current? Change in flux. So create change in flux in this. So put it on the table. So place it on the table, this silicon steel, small piece of steel, and take a permanent magnet, north south, and move that magnet near to the, so this is steel. So move near to that and take away from this. Move near, take away, move near, take away. But quickly you have to do for some duration, 2 to 3 minutes. Then if you do, what happened? North to south flux lines are flowing. When you bring near, more flux line will come into this metal, and when you take away, less flux line, more flux line, less flux line means there is a change in flux or not. Yes, you are creating a change in flux. Once there is a change in flux, EMF will induce or not? Yes. Once there is EMF, a current will circulate or not? Yes, current will circulate. That is nothing but eddy current. Now, due to that eddy current, after a small duration, you can observe the metal gets little heated up. Once heat is coming, now give that piece to them. Iron loss is there. So that means heat is generated. That's it. Small experiment. So, but all these small experiments we never conduct in our labs. That is our engineering. But everyone is same. I am also same like you. Okay. But we should have some practical information to understand, particularly electrical machines. That may be any rotating machine or anything. At least we should have some practical information. Then easily we can understand. Particularly construction parts. Induction machine construction, synchronous machine, DC machine, everything constructionally to understand clearly, you should have some information regarding construction of that machines. Means only in the labs we can see this. Only in labs. Induction machine at least we can see now outside. If you go to any service shops, ceiling fan or anywhere, motors, induction motor service shops, mostly induction motors you can see. But DC machine, synchronous machine is difficult to see outside rather than labs. Only in lab we can see that constructional parts. But we never observe all this. We will go to lab only for writing observations and records, just for gaining marks. Just like when there is a change in flux in any iron or conducting body, EMF will induce or not? Yes. When there is EMF, current will circulate or not? Yes, current will circulate because surface area available to circulate current. Now that current itself we call eddy current in the iron body, and that will cause some I square R loss. When there is a flow of current, definitely I square R loss will take place. But don't say this is copper loss, because this is not taking place in winding. So we given the name copper loss only when it is taking place in the copper winding. Okay, but not in iron. Okay, but not in iron or core. In iron or core, that I square R loss we call eddy current loss only. Next. Anything you should create, just variation you should create. You can move iron or by keeping magnet constant. Heat will not generate quickly, very slowly heat will generate. You try to do this after 5 minutes or, but quickly you have to do, not slowly, quickly. 2-3 minutes. After 2-3 minutes, little slightly heat will increase in that. Okay. Now let's see. Next, transformer core only we are talking. So first we have seen material, and then we have seen which type we have to use, solid or laminated. Laminated we have to use. Now let's see what is next is core staggering. Next heading, core staggering. Core staggering. Stagger means what? Arrange or attach. So core staggering simply nothing but it is the process of making a solid core into a laminated core. That's it. Making a solid core, cut it is into number of plates and then join. That is called staggering or attaching. So what is core staggering? It is the process of making a solid core into a laminated core. Is called core staggering. Write this. The process of making a laminated core by using laminated core from solid core. The process of making laminated core from solid core is called core staggering. Is called core staggering. Staggering means attach or join. So this core staggering in the construction side is very, very important. So in the manufacturing of transformers, any companies, if you visit, core staggering stage will be there. So that is very important stage. If staggering is not perfect, you will get so many problems in operation of transformer. Staggering should be very, very perfect. Now, what happens if you don't stagger properly? Don't stagger means what? We need to attach all the plates together tightly so that no gap should come between two plates. Can you join two plates tightly so that no gap will come? Maybe two plates only, no? That's why we can join so that no gap should come between the two plates. Yes, we can. Now there are hundreds of plates. So if you observe in this diagram also, so here we have nearly 20 plates. Now all the 20 laminations, can you attach tightly? Practically, it is not possible 100%. They will attach, but still there will be small gaps between some laminations. There will be small gaps between some laminations. Small gaps, thin air gaps will be there. Thin air gaps, small gaps will produce. So due to that, we get some problems here. So what are that problems? We will see now right here. Consequences due to poor core staggering. Poor core staggering. Suppose if the core staggering is not perfectly done, then we get some problems. So write that side heading. Consequences due to poor core staggering. If it is not perfectly connected, then what is the problems? So the first problem is what? There is possibility of thin air gaps. Thin air gaps, which causes. Now what is the problem of these air gaps here? What is the problem? So what is flowing in the core? Flux is flowing in the core. So when there is gaps, air gaps, reluctance will increase. Reluctance to the passing of flux increases. Reluctance will increase to the flow of flux. Whenever reluctance is, what is the magnitude of flux? Decrease. So if you want more amount of flux, what required? The transformer required more current from the supply only, no? Yes, if more current it is taking to generate more flux. Otherwise, if reluctance is less, for little current also you will get more flux. So the main first problem here is due to these small gaps, reluctance is increasing, which reduce flux in the transformer so that it will draw high currents from the supply. Whenever current increase, automatically I square R loss in the windings increase, then which reduce total performance of transformer. So this is the first drawback. So right here, which causes high current from the supply, high current from supply to produce the required flux, to produce the required flux. High current from the supply to produce the required flux. So high current, performance of transformer reduces. So this is the first drawback. Next, one more main drawback here is, so everyone knows this very well. Second drawback, that is, it will produce noise in transformer. It will produce a noise. What is the name of this? We call noise in transformer, we call humming noise. It will produce a noise called humming noise, also called magnetic hum, also called magnetic hum. Okay, it will produce a noise called humming noise or magnetic hum it is. So what is the main reason behind the noise in transformer? Poor core staggering. And what is that phenomenon we call? So write that point. The main reason for noise is, the main reason for noise is called, the main reason for noise is, so that is magnetostriction phenomenon. Important. Magnetostriction phenomenon. Magnetostriction phenomenon. The main reason for noise in transformer is magnetostriction phenomenon. So what is that magnetostriction? That depends on core staggering only. So what is magnetostriction? Let's separate that heading. Magnetostriction. Magnetostriction. So recently in engineering services also direct question on this magnetostriction. So what is magnetostriction? Why we are getting noise, and how this noise or where this noise depends. So everything clearly we see now. Observe. Magnetostriction. See, whenever there is gaps between laminations, that because of poor core staggering, as it is staggering not perfectly done, there is a chance of these gaps. Now what happens is, what is the nature of flux passing in the core? Alternating. Positive half cycle, negative half cycle. When there is a positive half cycle, flux will go in one direction like this. When there is positive half cycle, assume that flux is going in this direction. When negative half cycle, flux will come in opposite direction. What is the time duration for positive half cycle and negative half cycle? Just 10 milliseconds. No? Why 10 milliseconds? Yesterday also I said. What is the frequency? 50 hertz. Then what is the time period for one cycle? 1 by 50. Nothing but 20 milliseconds we get. Then for half cycle, what is the time period? 10 milliseconds. So within this small duration, flux is changing in the core. Flux, positive half cycle, flux clockwise, negative half cycle, anti-clockwise. So like this, flux is changing continuously in the core. Now during that, when there is gaps between lamination, plate to plate, when flux is moving, flux is nothing but the force only, no, that is magnetizing force, flux in this direction, other direction. So due to the change in the flux direction, these laminations slightly vibrate inside. These laminations will vibrate slightly. because of that change in the direction of flux quickly. You cannot observe. So you cannot observe that vibrations also, because 50 hertz means 50 cycles per second. So in 1 second, 50 times they vibrate. Can we observe? No, our eye cannot observe that. So in that much speed, the laminations are vibrating inside. That vibrations only we are getting as a noise in transformer. That phenomenon we call magnetostriction phenomenon. Okay, so write the statement of this clearly. Magnetostriction. Write the statement. It states that it states that whenever whenever a magnetic material is subjected to subjected to an alternating flux, then then there will be a slight changes in the dimensions of laminations, which is in the form of right up to this quickly. See, this magnetic material means core subjected to alternating flux. Because of this, the dimensions means what? That length and breadth slightly, that variations will be there. Slightly the laminations will vibrate there. So there is a slight changes in dimensions of laminations, which is in the form of vibrations. In the form of vibrations, which is in the form of vibrations, produces noise and produces noise. Okay, so this is we call humming noise or magnetic hum simply. Now how can we reduce humming noise? Yes, to reduce the humming noise you need to attach staggering. That core staggering should be perfect, means tightly lamination we should attach. Is it possible? No, practically 100% you cannot attach tightly. You mostly we attach, but still somewhere small gaps is possible. You cannot avoid this. That's why noise definitely will come from transformers. That small humming noise will be there. So one question to all of you. One question, because most of the people will not be aware of this. See, the question is, in which of the following, in which of the following humming noise will produce? Which of the following humming noise will produce? Answer: transformer, induction motor, synchronous machine, all of this. What is the answer? In which of the following humming noise will produce? Okay. Yes, good. Now, so as I am asking particularly, now most of you saying, okay, good. Option D, all of this. Otherwise, if I ask before this topic now, then what you will tell? Transformer, definitely. In where we get humming noise, definitely you will tell transformer only. But now particularly as I asked, now you said all. Okay, mostly right, all of you. Answer is all of this. Not only in transformer, but most of the people will think about only transformer. Not only in transformer, in induction motors also will get humming noise, synchronous machine also will get humming noise. But why we don't consider mostly there? So there we never discuss this humming noise in synchronous machine or induction machine. What is the reason? Because the humming noise in rotating machines is negligible. But in transformer, it is not negligible, because as transformer is static device, only humming noise will be coming from this, that is audible for us. But in induction rotating machine, you cannot observe humming noise, due to that bearing noise is more than humming noise. In your ceiling fan also in your home, humming noise will be there. Are you able to listen that humming noise? No, because that fan noise is more when compared to that humming noise. Rotating noise is more compared to that humming noise. If you want to listen humming noise, what you need to do is switch on the fan and stop the fan with any stick or by hand, and try to put your ear near to that. Then only you are able to listen humming noise. Otherwise, it is not possible. But don't perform like this for long duration. Otherwise, if you stop the fan for long duration, definitely it will damage, because that is under starting condition. What is the current run by motors at starting? Very high. Not only induction motor, DC motor also we know. At the time of starting, the induction motor or DC motor will draw little high current. So if you keep on holding that fan without rotating, definitely it will damage. Okay. So simply remember, wherever we have laminations, wherever we have alternating flux, their humming noise will be there. So transformer laminations are there, and nature of flux is what? Alternating. So humming noise. And induction motors, the stator and rotor laminated only, no? Yes, laminated only we use every AC machine, that may be machine or transformer, we use laminated core only there. So when there is laminations, when there is alternating flux, definitely there is humming noise. Okay. So in all these we have humming noise, but rotating machine we cannot observe. That's why we neglect. Make a note. Make a note. The humming noise or the noise in transformer, the noise in transformer depends on, so it depends on what? Noise in transformer depends on, where it depends? Air gaps. If gap is more noise will come. That is between laminations, if gap is more noise will be there. So it depends on magnitude of air gaps, magnitude of air gaps between laminations. Between laminations, if gap is more noise you will observe. Next, second. So same noise. So I said flux is changing. So whenever magnitude of flux increase, no, definitely noise also changes. So this is, you can observe in OC test in your lab. So if you observed, I think in OC test you can observe this. How? In OC test we apply rated voltage in your lab, if you remember this. So whenever voltage is increasing, now by auto transformer we will increase voltage there. So when you increase, slowly noise in transformer also will increase. So maybe if you remember this, if voltage increasing, noise also increases. More voltage, more noise will come. Less voltage, less noise will come. So whenever voltage is increasing, current in winding increase. Whenever current in winding increase, flux in the core increase. So more the magnitude of flux, more noise. Less magnitude of flux, less noise. So it depends on magnitude of flux. Magnitude of flux in the core. Flux in the core. So sometimes you may get flux, or sometimes they will give voltage, supply voltage. If voltage is more noise. So magnitude of voltage, magnitude of supply voltage. supply voltage. Okay, so based on this, noise will be there. Now how can you reduce noise? Tell me. Noise is there. Now how can you reduce noise in transformer? Don't say that by operating transformer at low flux magnitude. This is not desirable. We need high flux. If you operate at low flux, power transfer is reducing, efficiency also reduce. So we never prefer this. We operate at high flux only, no doubt. So we can reduce the noise by making as much as possible air gap is less, thin gaps as much as possible. We have to attach tightly so that noise will reduce. So only by this method we can reduce noise in transformer. See, this stage is very important in the manufacturing of transformer. So if you visit, you will come to know about this. At the final stage, after construction of transformer, they have testing stage. In the testing stage, if noise is more, no, definitely they will throw the transformer again outside. Means they will send the transformer to again reconstruction, because noise is very important criteria in transformer. The noise if coming more than their range, they will send it is to reconstruction, re-staggering again. They will open complete laminations again, re-staggering should be done perfectly. Okay, let's see one question in the previous engineering services. We got this question in the last year itself. See the question, read the question, and what is the answer? Tell me. What is answer? Yes. See, in this question, most of the students in this year, in the last year, most of the students, some of the students, by mistake given magnetostriction. By mistake, they placed magnetostriction. See, presence of mind is very important in examination. How much we prepared is not at all important. How much we presented during examination, that is the most important. So you may prepare very well, but presentation skill is very less. So no use of that. You prepared very less, but presented very well. That is best rank. So because during the hurry situations during examination, humming level or noise, once they observe, they will go to magnetostriction. So there only it is discussed, and they are not reading complete question and they are not understanding. So observe the question. The degree of humming level of the noise caused in transformer may be reduced by noise. How can you reduce noise? Here it is not asking what is the reason for noise. What is reason for noise? Magnetostriction. But they are not asking reason. They are asking how can you reduce? How can you reduce? One method is, if you reduce the supply voltage, it can be reduced. But is it desirable? So here given high flux density in core. High flux density means flux is more. If flux is more, noise will increase. It will not reduce. So this is not correct. So third, tightening of core by clamps. If you tight the core with clamps, suppose there is a laminated core, and to that core use clamps tightly, so that if they are tightly connected, no, the vibration will reduce automatically, noise will reduce. So this is the correct one. And quality of transformer oil. So oil is not at all reason for noise. Oil, it won't cause any reduction in noise in transformer. This is completely different. So answer is tightening of core by clamps. Okay. Yes, right. See, for engineering services, I already said we cannot say this particular topic important. Each and every line you should be perfect for the prelims examination. Each and every line you may get. So this is about core staggering of transformer. Okay, next, write about stacking factor. Next side heading, stacking factor. So this is indicated by Ks, stacking factor. See, what is the stacking factor? Where we use stacking factor. So stacking factor is the ratio of area of core, cross-sectional area of core. So what is the type of core we are using? Laminated core. So we are using a laminated core, like this. So laminated core we are using now. Now in this laminated core, do you have only iron material or only silicon steel is there in this? No. So we have silicon steel, at the same time we have insulating material in this. We have insulating material also. It is not only iron material, insulating material also we there. Now if you take cross section area here, cross sectional area, what is the cross sectional area? uh, if it is a square, I said as given yesterday, if it is a square core, no, if you know the side distance or magnitude, suppose a small a, what is the area of that cross section? A square, square area, a square, side square, no. So like that we are calculating. But when there is a laminated core, there are two areas here. We will define two areas. One is gross cross sectional area, gross cross sectional area, gross cross sectional area represented by AG, and other is net cross sectional area, net cross sectional area. So this is indicated with AN, and the relation between these two is called stacking factor here. So what is stacking factor is Ks. It is the ratio of net cross sectional area to the gross cross sectional area of core. What is net area and what is gross area? Let's see that. Net area. See, net area is nothing but it is the area occupied by only iron material, only iron, that is silicon steel here, only silicon steel. So in between we have insulating materials, and what is that insulating materials we are using? So these insulating materials are oxide paints, very very thin oxide paints we use as insulating material, or we use Japan varnish, we call varnish paints, Japan varnish, like this. These are insulating materials. And if you consider only silicon steel material, that is called net cross sectional area. Gross means what? Total area occupied by both iron and insulating material. So gross is nothing but iron plus insulating material, both will be there. So what is gross cross sectional area? It is the area occupied by both iron and insulating material. And what is net cross sectional area? It is the area occupied by only iron material. Okay, now right here, write the statement, stacking factor. It is the ratio of, it is the ratio of net cross sectional area to the gross cross sectional area of core. It is the ratio of net cross sectional area to the gross cross sectional area of core. And what is this value always? Ks is always less than 1, less than 1 for laminated core. less than 1 for laminated core, and it is equal to 1 for solid core. For solid core, it is equal to 1 because solid means there is no insulating material, solid iron itself. Net is same, gross also same. Then what is the Ks for solid? An equal to Ag only. Then it is 1. Solid core Ks equal to 1, and laminated core An is less. Ag will be more now. Gross it is total area. So it is always less than 1 we get. So mostly the value of this Ks will be in the range 0.9 to 0.99. In between these two will be there. Practically 0.9 to 0.99 stacking factor. Okay. Remember, don't forget all these words because in the EMF equation, all these terminology will come again. Next, next, next. Right now, difference between square core and stepped core. Right, the side heading. Difference between square core and stepped core. Square core and stepped core. See, all these subtopics is under transformer core only. So mainly two parts I said, transformer core and transformer winding. So whatever we are discussing now, all is under transformer core only. Okay. Difference between square core and stepped core. See, this is we are talking about cross section of core. That is important. So people will confuse in this square core and cross stepped core. This is about cross section. Cross section of core we are talking here. So I will show you clearly what is this. See this square core. We are talking about cross section. Don't confuse. This is not complete core. It is about cross section. See, this stepped core we also called cruciform core. The other name of stepped core is cruciform. Cruciform core. Okay, square core or stepped core. Now observe square core. See, first I will take transformer figure so that you will understand what we are talking here. Observe this. This is transformer core. Okay, complete transformer core it is. What we are talking here is we are talking about see in transformer core this vertical part, this vertical parts we called limb. These vertical parts we call limbs, and this horizontal parts we call yoke of transformer. This horizontal we call yoke. Okay, these horizontal parts are yoke and vertical parts of that core we call limbs. And where we place windings generally? Anywhere you can place either yokes or limbs, but generally we place the windings on limbs now. So here we are placing winding on the limbs. On the limbs we are placing winding like this. Now we are talking about cross section of that limb. So cross section of the limb we are talking. So simply you let us cut here, cut here. Just assume that this core limb is cutting at two points. Cut here, cut it, and take this piece outside as it is. So this piece is taken outside. Now let us, this is vertically. So for example, like this. This is the limb. This is the limb. So I will cut here, and this piece will come outside. Now I am talking about this cross section. this front cross section. Here only we place winding, no, like this, number of turns. So this cross section I am talking. This cross section is of two types. One is square cross section and one is stepped core cross section. So square cross section means like this, square. Okay, this is square core cross section. Here only we place winding like this. So I'm showing front view cross section I'm showing. This is vertical and this is front view I'm showing of this square. Now stepped core means you take the same square, same size of square first, same square take here and create steps in this at the corners of this square. Let's create steps like this. Steps are created. Okay, like this, steps created in this. Some two steps we created. Okay, two steps are created. Now let us place winding in both cases, square core and stepped core winding. Here we place winding, only one turn I am placing to compare. Now one turn I am placing. Here only we place winding like this. One turn, one copper wire, one turn is placed. Now in the same way, place one turn on this cross section. Place one turn on this cross section. Now in both cases, if you observe, in which case more copper wire is required, square or step? Yes, no doubt, square core required more amount of copper, more wire required for this, because what is this diameter? This is the diameter of this and this is the diameter of this, small d. So capital D is greater than small d. So whenever diameter increases, no, you require more copper wire. For each turn, you require more copper wire, more copper wire. Suppose there are 100 tons. How much copper wire total? So much. So more the tons, more copper is required for square. So write the first point here. It requires more copper for each ton, more copper for each ton. But in the stepped core or cruciform core, we call, it requires less copper. It requires less copper for each ton. Like that, if there are more tons, more saving in copper will be there for each ton. Right? Next. More copper required for square. Not only copper. Generally, if you consider this is the limb, if it is the limb, can you place directly winding on the limbs in any machine? Can you place directly winding on the cores? No. Directly copper winding you should not place here. Before that, what we have to place? Insulating material we have to place here first. If it is slots, rotating machines, in that also we place insulating material first, not directly coils or winding. So if it is the limb, first we will place a insulating material, just like paper. Let us take one paper, place throughout this first, and on that insulating material we will place number of tons. So what is the insulation required for square core? Because more diameter, more insulation required. Less diameter, less insulation is required. So in square core, right, it requires more insulation. It requires more insulation. Next, in stepped core, it requires less insulation. It requires less amount of insulation. Now what happened totally? Insulation is less in stepped core, copper requirement also less in stepped core. Then what is overall cost? Insulation cost reduce, copper cost reduce as size reduces, and overall the stepped core is preferred because it is less cost and maintenance also less. Cost is less mainly. So cost is reduces. Stepped core. But there is a problem of stepped core. Okay. So all of you clear this, what we are talking? So we are talking about cross section of the limb where we place winding. We are talking about cross section of limb where we place winding. This is two types. One is square core, one is stepped core. And some people may get doubt. You should get doubt also. What is that? Why we don't have circular core? Why we don't have circular core? Like square core, stepped core. Why we don't have circular core cross section? Yes, there is drawback. There is a drawback in circular core cross section. That's why we are not preferring that. What is that main drawback? Can anybody guess? Main drawback of circular core. See, actually here nearly 1,000 messages are there, so I am unable to search also. That is, scrolling is very difficult for me now. And particularly in online classes, interest required is more because uh, the students, whoever is listening, they cannot pay more attention because nobody watching you. So that is whatever you can listen, you can sleep, you can stand, or you can walk by listening also. And you cannot pay more attention towards class. But try to put more attention because it is not like physical classes. So this is your completely your interest. Based on your interest, you can listen. If you listen well, you can get. Otherwise, that much interest we cannot pay 100% just like physical classes. But as much as possible, try to put more interest. Yes. Okay. Turning of winding. Yes, good. Mangesh. The main problem of the circular core is designing of laminations is very difficult for us because these are all laminated cores. No, if it is a square core, see, if it is a square core, all laminations are same size, easily manufacturing. If it is stepped core, this is one size of lamination, this is second size, this is third size. Now here we have three different sizes of lamination. Okay, still we can manufacture. But if you consider circular core, now here we have so many different sizes of laminations. See, in circular core, you will get so many different sizes. So which will become very difficult construction. Construction will become very difficult for this. Different types of different sizes of laminations we have to design and we need to attach properly, that is. So constructionally it is very difficult. This is one problem. And other drawback of circular core is stiffness of winding will not be there in case of circular core. Stiffness. So you take yourself, take a pipe, take a square, any wood, wooden stick, anything, and take a copper wire and place on both, on the circular or any pipe you take some number of turns on that with copper wire, and take a wooden stick having square shape or rectangular shape, anything, and place some number of turns on that. Now try to drag the winding, on which case winding is perfectly placed tightly, square core or rectangular core. The winding will be tightly placed on that. That is, mechanical stiffness will be there for winding, but not for circular core. So due to all these reasons, circular cross section we never use. And we use stepped core with less number of steps, maybe 2 steps or 3 steps, not more steps. Again, if steps increases, no. Again, if steps increase, again different sizes of laminations will come, and that is also again difficult construction. For that reason, less number, 2 or 3 steps mostly we prefer, not more than this. Then what is the advantage of that stepped core? Less copper required, less insulation required, size reduce, cost of transformers reduce, which is economical. That's why we preferred this stepped core. Okay, so clear all of you this. This is about cross section. This is about cross section. Okay. For today's last topic we see force between current carrying conductors. Force between current carrying conductors. Okay, this topic we see in the transformer winding. So before that, I will give some important differences between transformer and induction motor. So write the setting. Difference between, see, transformer core is not completed. The first one is transformer core. Still, it is not completed. Still, we have one important topic, that is types of magnetic circuit. We have two types of cores. One is square core, one is shell type of core. Square core, shell type of core. Two cores we have. That is called core type and shell type simply. Whatever we are drawing now regularly, this one. Whatever we are drawing, this is core type transformer. And we have one more shell type. So the differences are regarding this we will see in the next class, and today we are completing this difference between, right, transformer and induction motor. Transformer and induction motor. See, once you learn transformers completely, no, 50% induction motor also you got. 50% almost same operation, and only little working principle will little change. And regarding equivalent circuit and whatever we see, no load and load operations, almost same for induction motor also. Okay, almost same. So tell me one important difference between transformer and induction motor. Try to guess one important difference, because when you face this question in any interview, no, don't tell static device, rotating device. That is a difference, but where is difference in you? Where is difference in you? Yes, one important difference. I'm searching for that important point. Yes. Okay. Okay. So many points you are saying. Frequency. Okay. Some of you saying about frequency. So that is the most important point. Okay. So many points you are saying good, but the main difference here is in the definition of transformer itself. I said constant frequency device, but induction motor is a variable frequency device. This is the first point you need to tell. Transformer is a constant frequency, no, because frequency will not change. But what is induction motor? Frequency will change. See, from primary to secondary, in case of transformer, frequency will not change, remains same. So we call it is constant frequency device. Constant frequency device, because primary frequency F, secondary frequency also same F. But in case of induction motor, supply frequency or stator frequency is F. But running condition, what is the frequency of this rotor in induction motor? ESF. That is called slip frequency. If stator frequency is 50 hertz supply, and this rotor frequency will be very, very less, in the range 2 hertz, 1 hertz, 3 hertz, like that. Very, very less. So much variation in frequency from stator to rotor, primary to secondary. But from primary to secondary of transformer, same frequency. So this is one important difference first. So it is a variable frequency device. Right, the first point in transformer. It is a constant frequency device. It is a constant frequency device. Next, induction motor. It is a variable frequency device. It is a variable frequency device. So why it is variable and all, you will see there in that particular topic. Just important points I'm raising here. Next point. Tell. Next, one more important is static dynamic. That is difference, but I will consider that point at the last only, because that is not big difference. That is a difference, but main differences I want. Now one more is, observe, from primary to secondary there is a continuous path for flux or not? Yes, flux is passing from primary to secondary continuously by core only. So low reluctance it is often, but in induction motor from primary to secondary, is there continuous path for flux? No. Stator, in the stator flux is passing low reluctance, but once it enters into air gap, it offers the air gap will offer high reluctance. Immediately flux little reduce, and again comes to the rotor body. So from stator to rotor there is no continuous circuit, but in transformer we have continuous magnetic circuit. Write that point. It has a continuous magnetic circuit, a continuous magnetic circuit. Next, induction motor. It has a discontinuous magnetic circuit. Means stator iron body, and again air gap, and again rotor iron body. So discontinuous it is, not continuous. Okay. Next point. Next. Next, one more important difference is this transformer will draw a current to produce the flux. That current we call magnetizing current. We will see that is in the next class. Just I'm giving magnetizing current. I mean, the current drawn by transformer to create the required flux is very less in transformer. That current we call I mu, magnetizing current, and that current is very less. In the same way, induction motor also will draw a current to create flux in the motor. That is also same magnetizing current, but this I mu is very high when compared to transformers, because this air gap will cause high reluctance. No, to overcome that high reluctance, it is taking very high current from supply, and that percentage is important. Current, magnetizing current drawn by transformer is very less, approximately 2 to 4 percentage of it. Approximately it is 4 to 5%. 4 to 5% of its full load current. But induction motor, the magnetizing current, I mu drawn by induction motor is very high, 25 to 35 percentage of full load current. Full load current means it's rated current. Compared to that, suppose rated current is 100 ampere, transformer will draw 4 amps, 5 amps, but induction motor will draw very high, 25 amps, 30 amps, in that range. This is due to air gap in induction motor. Next, one more main difference is power factor. At which power factor transformers will operate? Now, whatever the loads you are connecting to transformer, is there any specific load to be connected, or any load you can connect? Yes, any load you can connect. Like we have UPF load, or lagging power factor load, means RL loads, or leading power factor loads, means RC load, capacity loads. Any type of load you can connect to transformer, it will work. But at which power factor induction motor will operate? Induction motor always operates at lagging power factor only. Okay, there is no other power factor, because it operates only at lagging power factor. So why it is and all, you will see there in the particular topic right here. It can operate at any power factor. It can operate at any power factor. in transformer, that is. Next, induction motor, it operates only at lagging power factor. It operates only at lagging power factor. Okay, next. Can you operate transformer with a secondary open circuit? Tell me. Can you operate with a secondary open? See, secondary side I am open circuit it is. Can we operate? Yes, we can operate. That is itself OC test, no? One side is open, one side supply given. Yes, we can operate. Now, can you operate or can you run induction motor with a rotor winding open circuit? Suppose if rotor winding is open, is the motor will rotate? No. The motor will rotate only when this rotor winding is always short circuited. If rotor winding is open, motor will not rotate first. But transformer you can operate with the secondary open, you can operate. But induction motor with the secondary open, it won't rotate. Okay, write that point. It can operate. It can operate with secondary open circuit. With a secondary open circuit. Okay, we can operate transformer, no problem. But it cannot rotate. It cannot rotate. Motor will not start first. If you give supply also, it won't start. It cannot rotate with a rotor winding open circuit. With rotor winding open circuit. Because of this reason, in order to run the motor, the rotor winding, we call secondary winding of induction motor, that is rotor winding always short circuit. Then only induction motor rotates. Okay. Now you can write the last point as it is a static device, it is a rotating device, or it is a electromagnetic energy conversion device, and it is a electromechanical energy conversion device. So you can write the other points whatever you want. And make a note at the last. Make a note. Now, how can you treat an induction motor as a transformer? Induction motor also transformer or not? Yes. Induction motor is treated as a rotating transformer with a secondary short circuit. See, generally transformer secondary, we may open, we may short, we may connect load, anything. But induction motor secondary winding always short circuit. So with respect to transformer, if you compare, induction motor is treated as a rotating transformer with secondary short circuit always. Okay, so write that. Induction motor is treated as a rotating transformer with secondary short circuit always. With secondary short circuit always. Okay, induction motor is treated as a rotating transformer with secondary short circuit always. So these are some important differences between transformer and induction motor. Okay, so with this we stop here for today, and tomorrow we continue the same transformer core. It is not completed totally, still one more topic is left in that, that is the types of magnetic circuits. Two types, core type, shell type. So you'll see the differences between these two. Okay, and then we go to second part, transformer winding. So once it is completed, construction of transformer will be complete. Okay, tomorrow we see that. If you have any doubt today, you can ask. Yes, Nitesh.
Hello, good evening, sir. Sir, am I audible, sir?
Sirisha.
Hello, sir.
Nitesh, tell me.
Sir, transformer, why transformer is called as negative feedback circuit? Could you please once again explain me, sir?
Because according to generally feedback definition in control system, what is negative feedback is if the angle between input signal and output signal is 180 degrees, then we call
Yes.
it is negative feedback. No.
Yes, sir.
In the same way, in transformer, how much phase shift you are getting from input to output? 180 degrees.
Yes. Sir.
So we call it is a
Then
negative
how
feedback.
it? Yes, sir. How it will act as feedback, sir? That I want that one, sir.
That is due to Lenz law. According to feedback means what effect of output on input.
Yes, sir.
According to Lenz law, what is it? Lenz law is doing effect opposing the cause. Effect means what here? EMF induced.
Yes, sir.
What is cause for that? Flux.
Yes, sir.
What is cause for flux? Primary current.
Yes, sir.
What is the cause for that primary current? Supply voltage.
Voltage.
So effect means output, cause means input. Effect of output on input indirectly due to Lenz law.
Thank you.
Okay. Vaishnavi.
Sir, in 49F, sir. Sir, can you explain this first point again, sir?
If staggering is not perfectly done, then there is a possibility of small gaps between two plates.
Yes, sir.
Then when gap is there, what happens? Reluctance increase.
Increase. Yes,
When
sir.
reluctance increase, flux will decrease. No.
Yes, sir.
Then in order to produce same amount of flux, transformer will draw more current from supply.
Sir, flux and current are directly proportional.
More current, more flux.
Then here flux is less, no, sir. Then current also should be less.
Actually, flux is reducing. Okay.
Yes.
So if you want to produce more flux, transformer require more current or not?
What, sir? Can you say?
If it is required more flux in the core, the transformer should draw more current from supply.
Yes, sir.
That is the point I said.
Okay, sir. Sir, in 51F, sir. Sir, here in this humming noise will be produced due to alternating flux, no, sir?
Yes.
Then in
But you
synchronous
said the
machine.
synchronous machine DC flux, no?
Yes, sir.
But in the stator, what is the nature of flux? AC only, no?
Okay,
Stator.
sir.
Rotor flux is DC, okay. But what is the generating voltage? AC.
Yes, sir.
There AC current there, no?
Okay, sir.
That alternating current will produce alternating flux in stator, and that will cause humming noise in stator.
Okay. Sir, in a 34F, sir. In 34F.
30?
Sir, in this 34F.
Uh,
Sir, in this, I am getting current directions reverse, sir. I cannot able to.
which one? Which figure?
Sir, all figures, sir. I cannot able to apply right hand thumb rule, sir. I am getting reverse direction, sir. For all.
Primary side or secondary side?
In secondary side only, sir. In primary side, I am getting. In secondary side, I am not getting.
Secondary side, how you taken flux? The red lines.
Yes, sir.
Observe,
It is.
apply the red lines in the red line direction, thumb figure, and
Okay,
apply
sir.
your 4 fingers there in that winding.
In inverts means it is coming from right to left, sir. Arrow
Left.
is coming.
In the first figure, A, in A, your 4 fingers will go from left to right, no? Check in your
Sir?
in your figure, left to right, your 4 fingers is moving and curling.
Okay, sir. Left to right. We have to take inverts, sir. That fingers.
Left to right, front side, left to right, back side, right to left, according to figure.
Okay, sir.
You take a paper here and then you try to apply like this.
Okay, sir.
Okay. Amit Vikram.
So can you please provide your contact details?
Pardon?
So can you please provide your contact details?
So I provided in the first class itself. Rameshwari.
Good evening, sir.
Yeah, tell me.
Sir, once open 48F slide, sir. 48F. Sir, right side one example you tell in interviews that you explain with an example small iron piece. Once explain that, sir. I
So
didn't
simple
understand.
that take a small iron piece, maybe iron or steel, anything, and put it on the table because it should be stationary, and only magnet you can move up and but that is up and down. Because if you bring the magnet near to that iron body, flux lines will increase na, in that.
Yes, sir.
And when you take away that magnet, flux lines decrease.
Yes, sir.
Means magnitude of flux changing is there or not?
Yes, sir.
Yes. Then due to that, EMF will induce or not?
Sir, but it is only stationary. We didn't provide any supply, sir.
That is Faraday's law is there. No need of any supply. Faraday's law, flux, conductor cutting the flux, or flux is cutting the conductor. Anything, EMF will induce.
అంటే సప్లై ఇవ్వకుండా కూడా ఈఎంఎఫ్ అనేది ప్రొడ్యూస్ అవుతుంది సార్ జస్ట్
That is just like generator అదే కదా. In generator mechanical input you are giving and EMF induced, no?
ఓకే సార్
Same as it is.
అక్కడ హీట్ జనరేట్ అవుతుందని మనకు ఎలా తెలుస్తుంది సార్
That is just by touching the magnet, no? That is touching the iron body. If you touch the iron body, heat will little increase.
ఓకే సార్ థ్యాంక్ యూ సార్
Okay.
సార్ ఇప్పుడు డౌట్స్ మిమ్మల్ని అడగాలనుకుంటే మెయిల్ ఐడి కానీ మొబైల్ నెంబర్
నేను ఆల్రెడీ నిన్న ఇచ్చాను కదా, స్టార్టింగ్ తీసుకోలేదా?
నేను పీడిఎఫ్ చెక్ చేసి తీసుకుంటాను సార్
స్టార్టింగ్ లోనే ఉంది.
ఓకే సార్ థ్యాంక్ యూ సార్
నెక్స్ట్ నరేష్ నాయక్.
Sir, page number 38.
Tell me.
Sir, how did you get 100 the angle of minus 8?
This is primary to
Minus 80,
secondary.
and the angle of minus 30.
Secondary definition we applied. Secondary voltage lags the EMF, that is EMF induced is lagging the supply voltage by 180 degrees, no, phase shift.
Yes, sir.
That is I taken.
Okay. That's it, sir.
Okay. Pratyush. Who is this click?
Hello.
Tell me.
Page number 26, sir.
Click means what?
Class. My father is a photographer, so he named me.
26.
Yes, sir.
Tell me.
26, 24. Yesterday's class, sir.
Yesterday's one, 24 only it is. 23, no?
F.
This one?
Yes, sir. 26.
This one.
Yes, sir. Sir, why it is 18 into 13 plus 13? Why it is not 15?
Reluctance of core, no?
Yes, sir.
18 into 13, 18 into 3 means this 18, this 18, this 18. Okay?
Yes, sir.
3 18s plus 5 centimeter is air gap, but that air gap reluctance separately we are calculating here. 5.
Sir, 20, no, sir, it is.
Huh?
It is not 20. It is not 20.
Only mean length we are taking, not complete 20. Mean length, no, average we are taking, center to center.
Okay, sir.
Okay.
Thank you, sir.
Okay. Next, Meena.
Sir, once again explain eddy current.
This is whenever there is variation of flux in any iron body, EMF will induce in the core itself. We cannot find that EMF, and that EMF will cause a current in the iron itself. just like these currents is rotating like eddies in water, so we name it is eddy current. So when there is a flow of current, some resistance is offered to that current, and an I square R loss will take place. That is we call eddy current loss. In the form of heat, it will produce. Okay. Next, Meena. Tell me. Voice is not audible. Speak. Speak clearly now. Tell me. Voice is not clear.
Okay, sir. I will send you.
Okay. Okay. Next, Rakesh.
Good evening, sir.
Tell me, Rakesh.
Yes, sir. Sir, in DC machines, can we observe the humming sound, sir?
DC machine, because there also will be there, but almost it is negligible, because in the stator completely DC flux we don't have laminations there. So stator of DC machine not laminated first, so you cannot listen humming noise in that.
Okay, sir. Sir,
Only in AC machines we can listen if you stop rotating body.
okay. Sir, in 44F, sir, today's class.
20
44F, 44F.
44. Yeah.
Sir, there you'd said diagonal air gap more, no, sir. So flux is equals to mm by reluctance, no, sir. So the main reason for not passing through diagonal is air gap. Air gap is directly proportional to reluctance. Is that the reason, sir?
Yes.
Okay, sir. That's it.
Yes. Okay. Next, Dwarakesh.
Hello, sir.
Yeah. Speak loudly.
Sir, in 38F,
Uh,
how you found the secondary side phase angle and magnitude, sir?
This is 1:1
Secondary.
transformer, no? First one.
Yes,
1:1 means what? Whatever the primary voltage is there, secondary voltage also same magnitude. But why minus 180 is, we know the secondary voltage or EMF induced in the winding lags the supply voltage by 180, no?
Okay,
The
sir.
definition we have seen.
Okay, sir. In
Now,
1
second
to
one, 1:2 it is.
Okay, sir.
100 will become 200.
Okay, sir.
And minus 300 because minus 120 minus 180, total minus 300.
Okay, sir. Okay, sir.
Next, Pranjali.
Hello, sir.
Tell
Sir,
me.
in magnetostriction, we have alternating flux. So in positive half cycle, flux is
Yes.
clockwise or anti-clockwise.
Hmm.
Sir, in positive half cycle, clockwise or anti-clockwise flux.
Anything you can consider positive half cycle. Anything clockwise or any anti-clockwise, anything you can consider. If
Sir.
positive is clockwise, no, automatic negative will be anti-clockwise direction. That depends on sense of winding also.
Okay, sir. And sir, on only DC machine stator that is made of cast steel.
Yes, remaining all silicon steel.
So, sir, please give examples. Please repeat the examples of the rest all machines which are made of silicon steel.
Only stator of DC machine cast iron. Stator rotor of DC machine silicon steel. And induction machine stator rotor also silicon steel. Synchronous machine stator rotor also silicon steel. Transformer we can use both silicon steel and CRGO steel.
Okay.
Only stator of DC machine is cast steel.
Yes, sir. And in transformer we prefer CRGO steel. But sir, you gave example of rotating machine in which we use silicon steel like induction motors. So sir, more
Yes.
Please repeat examples of those rotating machines.
Means with respect to material, no?
Yes, sir. Silicon steel.
Like you
both.
give induction motor like that.
Not understand.
Sir, in transformer we prefer CRGO steel,
Hmm.
but in rotating machines we prefer silicon steel.
Yes, this is reason. Reason is what for this? Due to presence of air gap, na, in that.
Yes, sir. Sir,
Whenever
sir,
air gap is there, it is offering high reluctance. Whether if we use CRGO also, it has to cross that air gap anyhow. Then what is the benefits of using? If we use CRGO, you should get more benefit there, but you are not getting more benefit. You are getting unnecessary additional cost there. You are putting. For that reason, we no need to prefer CRGO for rotating machines.
Yes, and rotating machines mean induction motor and
induction motor or induction generator or synchronous generator, synchronous motor, anything.
Okay. And sir, last question. Sir, that interview question that you gave, so there we are to get iron losses in the steel. So there we are
current loss.
Sorry. So there we are using only one permanent magnet. But sir, we should use two permanent magnets, no, because otherwise two permanent
Yes.
there's no
More flux will be there. Heat will produce quickly.
yes, sir. And because we will get one north pole and one south.
Yes. First of all, we should get that idea is very important there.
Sorry?
We should get that idea na, first. Like that we can create.
Yes, sir. Yes, sir. Okay.
Yes, good.
Thank you, sir. Thank you.
Sunita?
Yes, sir. Sir, in transformer, you said that it has a constant flux. And transformer is a statically induced EMF.
Yes.
Sir, but the statically induced.
Here, constant flux means a magnitude of flux is constant, but it is variable, time variable flux. But magnitude, maximum magnitude of that flux is remains same only. Don't confuse in this. Constant flux means magnitude of flux remains same in the core magnitude, but it is time variable continuously. Okay, not DC. Okay. Srikanta Sahu. Hemant?
Sir.
Tell me.
Sir, in yesterday's class, sir, in Lenz law, we have taken two windings now, sir, primary and secondary. The effect is flux, na, sir, means producing opposite flux to the main flux.
Yes, finally, because without connecting load, effect is EMF.
Yes, sir.
After connecting load, flux will affect. Effect is the flux.
Yes, sir. Even same effect can be seen in first primary winding also, no, sir?
Yes, primary winding also. But there you cannot put current direction because EMF induced is little less than supply voltage. That EMF is opposing voltage, no? That's why current magnitude is less there. Otherwise, if there is no EMF induced, very high currents will flow in that primary winding.
Okay. And in 34F, sir, yesterday's class, 34F.
34 or 24?
34F, sir, in yesterday's class.
So that is little changed, I think. Which problem? This one?
Last problem. Yes, sir. Yes, sir.
Here
in primary winding, why we are not considering that inductive effect reactance, inductive reactance of the primary winding?
They did not mention about that leakage flux. They did not mention about reactance and all here. Only they given. So this is actual primary winding, and there is a resistor like this. This is given, and across this resistor directly they given voltage. So that is enough to calculate current.
But not even though that reactance will be there now.
It will be there. It will be there.
Then some voltage changes will be there.
Will be there, but directly across resistor they given voltage. If they given that voltage across impedance, no, then we have to consider reactance.
Okay.
Okay.
Thank you, sir.
Mr. Tulasi.
Hello, sir.
Tell me.
Sir, in 36F, sir. Sir, why particular 36?
Why?
Why it is not self-inductance, sir? Why only mutual inductance?
If you consider it is a self-inductance, you cannot find that E2 now first.
Sir,
Okay.
E2 is also equals to L into di by dt, no, sir? E self.
And that is depends on if you know the secondary self-inductance, then you can find.
Okay.
But we don't know now that is.
Okay, sir.
Okay.
Sir, how to eliminate the eddy current, sir? Like you asked the question.
Then you have to place complete insulating material. That
Okay,
means there is no flux first, there is no transformer action. Not possible practically, that is.
Okay, sir. Sir, in 40F, sir. Sir, here radiator tube and fins. Can you explain about that once?
Radiator tubes means like maybe you might have seen in your areas also tubes.
Okay.
Like this. In the same way, in place of that radiator tubes, in some places, we have like these fins. Fins means like plates. Plates
Okay,
will
sir.
be there, like this.
Okay.
Just like radiator tubes only, they will function. But in radiator fins, you will get more surface contact with air.
Okay.
You can
Okay,
see in outside transformer easily that is available.
Okay, sir. Sir, another doubt, sir. Here mirror view, we say no, sir. In conservative tank, we will see that what level oil is. Sir, but in breather also we will kept mirror, no, sir. Here mirror is not there, sir, in diagram.
This diagram. So, but in second, this one in separate breather, it is there, no? Here.
Yes, sir.
It is actual breather. The diagram is not clear in that.
Okay, sir. In this, how can we know that the oil level is changing, sir? In breather.
In breather, oil will not come. So if you observe this diagram, no, actually this pipe from the breather is above in the air. It is not in the oil. It is.
Okay, sir.
Clear?
Okay. Now I got it, sir. Sir, next in 43F, sir. Okay. Sorry. No, sir. Next. Sir, in 48F, sir. Sir, here, in that example you told, no, sir, square. How can we know that the currents that are formed only eddy currents, sir? Why can't we call them normal current?
Here in the iron body, what is the magnitude of that current compared to copper wire currents? Very, very small, no?
Yes, sir.
And these currents we cannot measure also. They are circulating. We cannot measure that currents also.
Currents.
That's why.
Here, conductor is only the iron core only.
Iron having less conductivity, not like copper.
Okay.
There is some conductivity to this.
But it is. Okay. In 50F, sir. Sir, can you please explain about magnetostriction?
This is the like whenever any magnetic material, if you subject with alternating flux, so what is happening in the material for every half cycle, laminations is vibrating, no?
In diagrams.
Which one? This one.
Magnetostriction in diagram.
Here.
Okay.
Yes. So whenever flux is changing, positive half, negative half, the flux direction will change. Flux is nothing but a force, no? Then whenever flux direction is changing, laminations will vibrate there because of small gaps. Suppose if there is no gap, no, is the lamination will vibrate?
No, sir.
No, no chance, because for vibration there is no chance, tightly connected. Then noise will not come.
Okay. Thank you, sir.
That phenomenon is magnetostriction.
Okay. Thank you, sir.
Hello. Tell me.
Hello, sir. Am I audible to you?
Yes.
So I want to ask that if you do hot rolling of silicon, so whether there will be any difference?
You don't get orientation, rather than you will get so much non-orientation. So first of all, at very high temperature, silicon steel is not in proper state, no.
Acha. So means sir, according to material we will vary. Means we will look whether we have to do hot rolling or cold rolling, right?
Yes, only in cold rolling we are getting what we require.
Acha. And then sir, we don't do usually means we don't use hot rolling.
No, that is for some other application, but not here. Now, hot rolling we do in if you go to any steel industries, no. For hot rolling, what is the main purpose of hot rolling? To design shapes.
To design means
any desired shapes for any metals.
Acha, means that also will deal with crystal structure only, no?
Yes, manufacturing stage.
Okay.
If you visit any steel industries, if you look in Google also, you will get idea.
Okay, sir. And so one more question regarding last session. That 8F slide, sir.
Which one?
8F.
8.
Yesterday's session.
8. Number?
Yes, sir. That I'm not getting that, sir. How E2 and E1 are in phase? Means how E1 get
what is the reason for E2 and E1? Flux only, no?
Yes, but sir, my question is that E1 will relate with V1, no, sir? Means voltage, applied voltage.
See, this EMF E1 and E2 both opposing supply voltage. When E2 will oppose? If you connect a load, it is producing a flux. So like that, it is opposing primary.
Means sir, you're saying that after applying voltage, we will get E1 also, means after some shift.
Yes, suppose V1 is at an angle 0, no? Then E1 will be at an angle -180, and E2 also at an angle -180. E1, E2 in phase.
Yeah.
Which is lags supply voltage by 180 degrees. Because reason is same, now, for both E1 and E2. EMF in primary and secondary. Reason is what for both? Same, flux only.
Okay.
Yes,
thank you so much.
Both are in phase.
Thank
yes.
you, sir. Thank you.
Muhammad, who is this?
Sir.
Tell me.
Sir, in page 38F, sir, that voltmeter problem.
Yeah.
Sir, turns ratio means N1 by N2, na, sir? In general, I studied.
Yes, sir. Turns ratio, it will come in the next classes. Turns ratio is N1 by N2. Transformation ratio is N2 by N1.
Sir, but here it indicated 1:2, means turns ratio equal to 2, but in question it's given.
Actually, it is transformers 1 and 2, I think, not turns ratio directly. So this is mentioned, not turns ratio directly in the figure.
Okay, that question is wrong, na, sir.
Yes,
I'm telling you about second one only,
right.
2. Okay. Clear, sir. Sir, one more, sir. Sir, if in fringing effect, the question paper who designed, he only will give the cross section.
They will give cross section. Otherwise, we cannot find.
Okay, sir. Sir, this V1 and E1 induced EMFs are there, na, sir? V1 is the supplied voltage, E1 is the induced in primary, E2 is induced in secondary. Sir, since E1 the primary is closed path, the induced current will flow through it, sir?
Yes. Induced current means actually EMF E1 also will cause a current, but this source is little greater, no? Because of some drop in the winding, V1 is greater than E1. So this E1 is opposing voltage, so that current is limited there. Otherwise, if you take EMF is 0, for example, V1 is there, E1 is 0. Now what happened? Tell me here. What is I1? I1 equal to directly V1 by the resistance of this.
Yes, sir.
Then very, very, very high current will flow. Resistance is very small now for this copper windings we use. Low resistance. Now what happens when there is EMF E1, V minus E1.
Okay, it means it will be there. Okay, sir.
Yes, just like back EMF in motors. It will limit the current in windings.
Okay. Sir, again in 36F, sir. Sir, in that one of the friend asked that if it is given L, then you said that we can find. Sir, but
Yes.
for that the current should flow through the secondary winding, sir. L2
Yes,
di2
yes,
by dt.
yes. Then only we can find.
Okay.
Yes,
Okay,
right.
Thank you, sir.
Okay, last Subhash.
Sir, permeability and relative permeability explain, sir, once.
Permeability is total permeability, which is the combination of free space and relative permeability. Relative permeability is what? This is mu naught. Relative permeability is calculated with respect to some other material. So we take reference is air. What is the relative permeability of air? 1.
1.
Then we will compare the permeability of some other material with respect to this relative.
Oh, okay.
Like that we calculate relative permeability with respect to other material.
Okay, thanks.
Okay. So closing the session. Tomorrow we meet at the same time.
Excuse me, sir. One doubt, sir.
Who is this?
Yeah, Rakesh, sir.
Rakesh, tell me.
Sir, in that EMF pattern, you said no, sir. Like 100 by 200, it starts at 0.5. If that 100 volt supply is given between the other two turns, sir, then which one should we take, sir? EMF pattern.
That only. Wherever you apply, that is only you have to calculate, and that is applied for the other windings.
No, sir. Supply 100 volts is given at the primary, no, sir. So if I mean to tell, like two separate winding, 3 are there, sir, separately 3 windings.
Okay.
So which one should I consider at the point where the supply is given?
Wherever you given, that is only.
So if the supply is given at the second winding, if I 100 by 101.
Yes, 1. Then apply for other same.
So EMF pattern is constant.
Yes, same. So that will come in the next coming topics. EMF pattern same in transformer.
Okay, sir. And regarding that blocked rotor test, sir, what exactly happens in that?
Which induction motor?
No, yeah, induction motor, sir. Like we are stopping, no, sir. We in our lab.
When you stop, how much voltage you are applying at that time? Very small voltage we apply, because blocked rotor means short circuit, that is.
Yes, sir.
When you stop there, just like transformer short circuit test, it is almost similar.
Okay.
So as we are applying small voltage, high currents will flow. At there, in that situation, you can observe humming noise in induction motor.
Okay, sir.
Okay, under running condition, not possible.
Okay.
You will see that is in short circuit test clearly. Okay.
That's it. Thank you.
Okay, good night.